Hello and welcome to Sleep Science Space, a quiet place where curiosity is invited to slow down, soften its edges, and gently rest. Tonight we're going to drift together through something vast, something ancient, something so enormous that it stretches far beyond anything we can see, yet somehow feels deeply personal. We're going to explore our home galaxy, the Milky Way, and gently unfold a question that sounds simple at first, but becomes more mesmerizing the longer you sit with it. Just how big is our galaxy? When you step outside on a clear night, far from the noise and glow of city lights, you may notice a faint milky band stretching across the sky. It doesn't shout for attention. It simply rests there, a soft ribbon of light, like mist brushed across the darkness. That quiet band is the Milky Way itself, the combined glow of billions of stars, so distant, so densely packed, that your eyes can't separate them one by one. Instead, they blend together, dissolving into a shimmering haze. You are seeing the galaxy edge on, the vast disk that we are already inside of. For thousands of years, humans have looked at this glow and wondered what it truly was. They told stories about it. They imagined celestial rivers, pathways for spirits, traces of gods crossing the heavens. And now, with modern science, we can begin to measure it, map it, and describe its shape. Yet, even with all our instruments and equations, its true scale still slips easily beyond intuition. Before we drift any further into numbers and distances, let me ask you something. Where are you listening from right now? Are you in a city where streetlights wash out all but the brightest stars, or somewhere quieter where the Milky Way still arches clearly overhead, bold and unmistakable? Maybe you're indoors, warm and still, letting the night sky exist only in your imagination. Wherever you are, one thing is certain: you are already inside the structure we're about to explore. You're not observing from afar. You're traveling within it, carried on a small planet, circling a modest star, all of it moving together through a grand spiral of stars, gas, and dark matter. If this gentle journey feels calming, if it helps your thoughts loosen their grip on the day, you're welcome to like this video or subscribe. It helps this quiet corner of the universe reach others who may also be searching for a peaceful place to rest their minds. And tonight, you don't need to remember every detail. There's no test waiting at the end. Just let the immensity of it all pass by the way waves roll in and out without asking anything from you. So let's begin somewhere familiar: Earth. Our planet feels enormous when we think about oceans stretching thousands of kilometers, or continents that take hours to cross by plane. But next to the sun, Earth becomes surprisingly small. You could line up about 100 Earths across the sun's face from one side to the other. And even that glowing star, the center of our daily lives, is only one among hundreds of billions within the Milky Way. The sun is not especially large. It's not unusually bright. It's a fairly ordinary star, quietly orbiting through the galaxy's disk, one among countless others doing the same. If you could shrink Earth down to the size of a single grain of sand and place it on a beach, the sun beside it would be about the size of a grapefruit, a gentle reminder of how scale changes, depending on where you rest your awareness. Now let that image soften and expand. Imagine not just a handful of grapefruits, but billions upon billions of them scattered across an entire continent. That begins to offer a quiet intuition for how many stars surround us. The Milky Way contains somewhere between 100 and 400 billion stars, depending on how we count them. And that number may rise even higher when we include the faintest, smallest stars, those that glow gently at the edge of detection. The number alone is almost dizzying, but the deeper question is not just how many stars there are, it's how much space they occupy. The main disk of the Milky Way stretches roughly 100,000 light years from side to side, give or take depending on the measurement. That means if you could travel at the speed of light, the ultimate speed limit of the universe, it would still take 100,000 years to cross it. And that's not a slow journey. That's light itself moving as fast as nature allows. For comparison, light from the sun takes about 8 minutes to reach Earth. Now imagine those 8 minutes gently stretched and stretched until they become 100,000 years. That shift alone begins to hint at the immensity of our galaxy. Still, even a number like 100,000 light years can feel abstract. Our sense of distance is built on familiar experiences, car rides, flights, long drives across countries. A kilometer, 100 kilometers, perhaps a few thousand, even millions still feel human. A million steps, a million grains of rice. But a light year exists far beyond everyday intuition. 1 light year is about 9.5 trillion kilometers. If you were to drive a car at highway speed around 100 kilometers per hour without stopping, day or night, it would take more than 10 million years to cross just a single light year. Multiply that by 100,000, and the Milky Way begins to feel less like a place and more like a vast, quiet realm stretching beyond imagination. As all of this unfolds, remember that the sun carrying Earth along with it is not standing still. Our entire solar system orbits the center of the Milky Way at a speed of roughly 828,000 kilometers per hour. That sounds incredibly fast. Yet the galaxy is so vast that even at that speed, one full orbit takes about 225 to 250 million years. This period is sometimes called a galactic year. That means that throughout the entire history of humanity, from the first stone tools to modern space telescopes, our solar system hasn't even completed a fraction of a single lap around the galaxy. The last time the sun was in roughly this same region of its orbit, dinosaurs were still walking the Earth. So when we think about scale, it's not just about distance, it's also about time. Time flowing slowly, patiently, across cosmic paths far longer than any human story. And size itself is more than width. The Milky Way is not a flat plate of stars. It has depth, layers, structure. The thin disk where most stars reside is about 1,000 light years thick. Beyond that lies a thicker disk, and beyond that, a vast halo populated by ancient stars, globular clusters, and invisible dark matter. This halo may extend 300,000 light years or more from the center, which means the true size of the Milky Way depends on how you define its edge. There is no sharp boundary, no clear wall. The galaxy simply fades outward, stars growing farther apart, until at some gentle threshold they are influenced more by neighboring galaxies than by our own. Even the name Milky Way carries softness, something poured, something flowing across the sky. In ancient Greece, it was said to be milk spilled from the goddess Hera. In China, it was the river of heaven separating two lovers who could meet only once each year when birds formed a bridge. In Finland, it was known as the pathway of birds. Across cultures, across centuries, people named it with wonder. They could see its glow, but not its individual stars. Now we know that glow is the blended light of billions of suns overlapping and blurring together, and even that simple fact quietly hints at just how immense our galaxy truly is. If you were able to isolate a small patch of the night sky no wider than the moon and patiently count every star belonging to the Milky Way within that circle, you wouldn't find just a handful. You would find thousands. Those stars are spread all along the pale band we see stretching across the sky. And when that narrow slice is multiplied across the entire disk of the galaxy, the numbers rise naturally into the billions. But the size of the Milky Way is not defined by stars alone. Between those points of light lies vast space filled with gas dust and something we cannot see at all, dark matter. Immense clouds of hydrogen extend across many light years, slowly drifting, slowly cooling, and in some regions collapsing under gravity to ignite the birth of new stars. Tiny grains of dust, far smaller than a human hair, gather into enormous lanes that wind through the galaxy. These dark bands absorb starlight and create the shadowy streaks you may notice cutting through the Milky Way's glow. They are not empty gaps, they are dense regions where light struggles to pass. Because of this, seeing the far side of our own galaxy has always been difficult. For a long time, astronomers didn't even know the Milky Way's true shape. After all, we are inside it, looking outward through layers of gas and dust. Only by carefully measuring the positions of stars, mapping radio signals from hydrogen gas, and more recently using space missions like Gaia, which tracks stellar motion with, with extraordinary precision, have we begun to assemble a clearer picture. And even now, that picture is not complete. When we ask how big the Milky Way is, the answer depends on what we choose to include. Are we counting only the visible disk of stars, the extended halo of ancient globular clusters, or the vast invisible structure of dark matter whose gravity may outweigh all the stars combined? If everything is included, the Milky Way's full reach may approach 1 million light years across. Yet the familiar glowing band, the disk we see in the night sky, remains closer to 100,000 light years wide. Both descriptions are accurate, each from a different point of view. The difficulty lies in the limits of human intuition. We evolved to judge distances that could be walked, climbed, or crossed in a day. Meters feel natural, kilometers still make sense. But when distances stretch into thousands of trillions of kilometers, our minds need help. So imagine shrinking the entire Milky Way down to the size of a dinner plate. In that scale, our entire solar system from the Sun outward past Pluto and beyond would be smaller than a single grain of sand resting on its surface. That is how small our neighborhood is compared to the galaxy that contains it. Thinking about this can feel overwhelming at first, but it can also be quietly comforting. The galaxy is so vast, so ancient, that the pressures of a single day begin to soften. Things that feel enormous over a week or a month grow smaller when viewed against hundreds of thousands of light years and hundreds of millions of years of slow galactic motion. It's like hearing the ticking of a small clock while knowing that beyond the room lies the ocean. The clock matters. The ocean exists. Both are real. Even now, astronomers continue refining our understanding of the Milky Way's size. Surveys like Gaia are mapping billions of stars, building the most precise three-dimensional model of our galaxy ever created. With each update, distances become clearer, the shape of spiral arms sharpens, estimates of the galaxy's total mass improve. Current measurements suggest the Milky Way holds between 1 and 2 trillion times the mass of the Sun, most of it hidden in dark matter. That mass shapes the motion of stars, governs the paths of smaller satellite galaxies, like the Magellanic Clouds, and even influences a distant future encounter with the Andromeda Galaxy billions of years from now. So when we ask how big the Milky Way is, we're really asking many questions at once. How many stars does it contain? How wide is its disk? How far does its halo extend? How much mass lies hidden in darkness? How long does it take for stars to complete their orbits? Each question offers a different answer. Together, they describe a structure so vast that language itself begins to stretch. And yet, you are part of it, not outside, not separate. Every breath you take, every heartbeat, every coded thought happens while you are circling the galactic center at hundreds of thousands of kilometers per hour. You are riding a spiral arm of the Milky Way, a passenger within a system of unimaginable scale, and that awareness alone can gently deepen curiosity or simply allow the mind to rest. When you step outside on a clear night and allow your eyes to slowly adjust to the darkness, you may notice a faint arc stretching quietly across the sky. It doesn't resolve into individual points of light. Instead, it appears as a soft, luminous river, wide, hazy, and continuous, flowing gently from one horizon to the other. That subtle arch is the Milky Way seen from the inside, and it is one of the most remarkable sights the human eye can witness without any instruments at all. Many people who grow up surrounded by city lights never see it clearly. Street lamps illuminated buildings, and glowing signs wash out its delicate glow, leaving only the brightest stars behind. But in places far from artificial light, under truly dark skies, the Milky Way reveals itself in full presence, often leaving first time viewers quietly stunned. For thousands of years, this glowing band has inspired myths, guided travelers, and stirred deep questions in the minds of philosophers. Today, we understand that what looks like a pale river is actually the combined light of billions of distant stars blended together by the limits of human vision. It's a little like trying to count grains of sand on a distant beach. From far away, the details vanish, and all that remains is a smooth, continuous blur. Each tiny shimmer within that glow is a star system, many with planets of their own, spread throughout the disk of the galaxy, and we are embedded within one of its spiral arms. So, what we're really seeing is an edge on view of our galactic home. When you look at the Milky Way stretching across the night, you are gazing through the densest regions of the disk, peering through layer upon layer of stars, gas, and dust. Ancient cultures tried to make sense of this sight in the language of story. The Greeks imagined it as milk spilled across the heavens, giving rise to the name Milky Way. In India, it was sometimes called the Ganges of the sky, a sacred river flowing above Earth's own. In the Americas, some indigenous peoples saw it as a trail walked by spirits. Each name reflected how the band appeared and how it fit into the culture's understanding of the world. Long before telescopes, before photography, people could only guess at its nature. Some thought it was fire, others believed it was a seam, a place where the sky itself had been stitched together. What united all of these interpretations was the same recognition this was something vast, something beyond ordinary experience. That understanding took a dramatic turn in the early 1600s when Galileo turned one of the first telescopes toward the Milky Way. The hazy glow dissolved into countless individual stars. For the first time, humanity realized that the soft band in the sky was not mist or vapor, but the light of innumerable suns. Since then, each new generation of instruments has added another layer of clarity. Larger telescopes revealed structure. Photographic plates captured faint regions invisible to the naked eye. Radio astronomy traced vast clouds of hydrogen gas across the disk. Infrared telescopes pierced through dense dust, and space observatories began measuring stellar positions with extraordinary precision. With every advance, the Milky Way became less mysterious, and yet, in many ways, even more immense. Together, all of these observations have shaped the picture we hold today, a vast spiral galaxy with sweeping arms, a dense central bulge, and a wide halo of stars surrounding it all. Yet, even without instruments or data, simply standing beneath a dark sky is enough to sense that immensity. The Milky Way curves overhead as a quiet reminder that we live inside something far larger than ourselves. When you look up, you are peering into the thickness of the galactic disk, receiving light that has traveled tens of thousands of years to reach your eyes. Each glance becomes a kind of message from the distant past. Some of the stars whose glow you see may no longer exist. They may have burned out or exploded long before the first humans ever appeared on Earth, and yet their light continues on arriving only now. In this way, the galaxy is vast, not only in space, but in time. The river-like appearance of the Milky Way is shaped by dark lanes that run through it. These shadowed regions are dense clouds of interstellar dust blocking the light of stars behind them. To the naked eye, they appear as ragged gaps, like torn fabric laid across the glow. In reality, these are cold reservoirs of gas and dust, places where new stars may one day be born. They are stellar nurseries, quietly hiding the earliest stages of new systems. Through a telescope, the Milky Way reveals even more detail. clusters of young blue stars, glowing nebulae, ancient red giants nearing the ends of their lives. The galaxy is not uniform. It is a varied landscape with each region telling a slightly different story about how stars form, evolve, and fade. The sheer number of stars remains difficult to comprehend. Imagine standing before a vast city skyline at night, every window illuminated. Now multiply that scene by thousands, then by tens of thousands, and you begin to approach what is contained in a single broad sweep of the Milky Way. When astronomers estimate how many stars the galaxy holds, they don't count them one by one. Instead, they measure how densely stars are packed in a small region, then carefully extrapolate outward. That is how we arrive at estimates ranging from 100 to 400 billion stars. And even then, stars may only be part of the story. The Milky Way likely contains billions of planets, perhaps even more planets than stars, especially if small rocky worlds like Earth are common. So when you look up at that pale band of light, you are not only seeing stars, you are glimpsing a vast galactic ocean of worlds. What makes the Milky Way visible to the naked eye is not just the presence of stars, but the way they overlap. Individually, stars appear as points of light. Together, they blend into a continuous glow. Your eyes cannot resolve them separately. That blur itself becomes a quiet measure of scale. The faint light you see is the combined aureole of photons from immense distances packed closely enough that they merge in your vision, a natural demonstration of cosmic crowding. The appearance of the Milky Way also depends on where you stand on Earth. Near the equator, it can stretch nearly overhead, forming a clear arch from horizon to horizon. At higher latitudes, it appears tilted or lower against the sky. And at certain times of year, the brightest and densest region of all comes into view, the galactic core shining in the direction of the constellation Sagittarius. During those months, the Milky Way appears especially rich, with a gentle swelling of brightness marking the region where the galactic center lies. This area is densely packed with stars and glowing nebulae, and hidden deep within it sits a supermassive black hole known as Sagittarius A star. None of this is visible to the naked eye, and yet the increased brightness offers a subtle clue to the galaxy's structure, a quiet hint that something dense and powerful resides at its heart. The Milky Way itself is not unusual in form. If you could step far outside our galaxy and look back from a distance, it would resemble many other spiral galaxies scattered throughout the universe. Galaxies such as Andromeda or the Whirlpool Galaxy give us a glimpse of what our own home might look like from the outside, a glowing disk with graceful spiral arms, a bright central bulge, and faint extensions reaching outward into space. From Earth, however, we never see that full picture. We experience the Milky Way only from within as a band of light overhead. That limitation is one of the reasons it took astronomers so long to understand its true shape. For much of human history, the Milky Way was thought to be the entire universe. The idea that countless other galaxies existed beyond it was not widely accepted until the early 20th century, when astronomers such as Edwin Hubble demonstrated that spiral nebulae were actually distant galaxies far outside the Milky Way. The scale of reality expanded dramatically. What had once been called the universe became just one galaxy among billions. And yet the Milky Way did not lose its significance. It remained our home, a river of light arching across the sky. Its vastness did not shrink when placed in a larger cosmic context. Instead, it gained meaning, a sense of belonging within something even greater. It's worth pausing to reflect on how we perceive that glowing band compared to what it truly represents. When you look at the Milky Way, you are not seeing the whole galaxy. You are seeing its densest slice, the region where your line of sight passes through the greatest concentration of stars. You are looking at the galaxy edge on. If we could observe it face on, it would appear as a majestic spiral. From inside, we experience only the side view, like standing in a vast forest and looking between countless tree trunks. The forest feels endless, but your view follows just one narrow path. The river metaphor works in another sense as well. Just as a river carries water so downstream, the Milky Way carries stars, gas, and dust in steady orbit around its center. Everything you see in the night sky, every star visible to your eyes, is part of this immense flow. We are immersed within it, carried along without choice, circling the galactic core. The motion is far too slow to feel directly, but over millions of years, this galactic river quietly shapes the fate of stars and worlds alike. The appearance of the Milky Way also changes with altitude. High in the mountain above much of Earth's atmosphere, the band appears sharper and more detailed. That is why astronomers have long sought high dry locations for their observatories. Peaks in places like Chile, Hawaii, and the Canary Islands rise above the haze, allowing clearer views of the sky. From these heights, the Milky Way reveals finer structure, and even faint features begin to emerge. And yet the essential sight, that glowing band stretching across the darkness, is available to anyone willing to step outside at night. It is one of the few cosmic spectacles visible without any equipment at all. For many people, the first clear view of the Milky Way is deeply transformative. For those accustomed to city skies, the experience can feel overwhelming. Some even report a sense of dizziness, a kind of quiet vertigo when confronted with so many stars. Psychologists sometimes refer to this response as a version of the overview effect. Astronauts describe a similar feeling when seeing Earth from space. It is a mixture of awe, humility, and at times a gentle unease, the realization that you are inside a galaxy filled with billions of suns. But beneath everything else, what remains strongest is wonder. It is that sense of wonder that has always driven humanity forward, to ask questions, to build instruments, and to search for understanding beyond the limits of the familiar. What's striking is that no matter how much we learn, the Milky Way still evokes the same feelings it did centuries ago. Knowing that the glowing band is made of billions of stars does not make it less beautiful. If anything, it deepens the experience. The light above you is not simply decoration in the sky. It is evidence of structure on the largest scales imaginable. A quiet reminder that you are part of something vast and enduring. The river of stars stretches on in silence, crossing the sky while we slowly turn beneath it. With each rotation of Earth, a different portion comes into view. The Milky Way is always there, but we meet it from changing angles, different seasons, different hours of the night. That slow shift has long given rhythm to human life. Farmers once watched the stars along the band to mark the passing of seasons. Sailors used it to find their way across open oceans. Even today, surrounded by digital clocks and satellites, the Milky Way still stands as a quiet marker of time and place. Its vastness is not only a matter of distance, but of history. The stars that form its glow span immense ranges of age. Some are newborns, only a few million years old. Others are ancient, shining softly after more than 10 billion years. Some burn blue and hot, destined to live fast and fade quickly. Others glow red and cool, expected to endure for trillions of years. Together, they form a population that tells the story of the galaxy's past and offers hints about its future. To see the Milky Way is to witness billions of timelines at once. Each star carries its own lifespan. Each point of light represents a different chapter in the galaxy's long narrative. And so, when you look up at that river of light, remember that you are not separate from it. You are inside it. The atoms in your body, the breath you just took, the thoughts drifting through your mind, all of it is happening within this immense structure. You are one of countless beings living in one of countless systems moving as part of the river itself. If you have ever tried to count stars on a clear night, you already know how quickly the task becomes overwhelming. You choose a small patch of sky, begin with the brightest points, and soon notice dozens more hiding quietly in the background. By the time you reach a few hundred, your eyes begin to tire. The points blur together, the numbers lose meaning. Even under the darkest skies, the human eye can see only a few thousand stars at most. That may sound like many, but compared to the true population of the Milky Way, it is barely a trace. Our galaxy holds hundreds of billions of stars, perhaps even more, if faint red dwarfs are as common as current evidence suggests. And when astronomers speak of hundreds of billions, they are not counting them one by one. These numbers emerge from careful estimates built patiently from observation measurement and quiet inference. The process begins in a simple way. Astronomers first measure how many stars appear in a small, carefully chosen patch of sky. Then, using what we know about stellar brightness and distance, they gently scale those numbers upward. It's a bit like stepping into a forest, counting the trees in one clearing, and then using that information to estimate how many trees the entire forest might contain. The method is not perfect. Some regions are hidden behind thick curtains of dust. Others are so densely packed that individual stars blur together even through powerful instruments. But with modern telescopes, especially those in space, capable of seeing wavelengths beyond visible light, these estimates have become steadily more reliable. Counting stars is not only about numbers, it is also a way of asking what kind of galaxy we inhabit. A galaxy's size is defined not just by how wide it is, but by how many stars it holds. With hundreds of billions of stars, the Milky Way is considered a large spiral galaxy, though not the largest known. Other galaxies, such as Andromeda or enormous elliptical galaxies found in dense clusters, may contain a trillion stars or more. Still, for us, the Milky Way is vast enough, immense enough, that its population already stretches far beyond comprehension. To place those numbers into perspective, imagine each star as a single grain of sand. 100 billion grains would be enough to fill several Olympic sized swimming pools. Spread across a shoreline, they would extend in for kilometers. Now imagine trying to count each grain one by one. That is the scale astronomers are working with when they speak of the stars in the Milky Way. And yet, when scientists count stars, they do not think of them as identical grains. Each star is a sun with the potential for planets, moons, and perhaps even life. Counting stars is, in a way, counting possibilities. Each one represents a system that may never be seen directly, yet almost certainly exists. This question has fascinated people for centuries. More than 2,000 years ago, the philosopher Democritus suggested that the Milky Way might be made of countless distant suns. Others imagined it as mist fire, or even a seam stitched into the sky itself. It was not until Galileo aimed his telescope upward that the truth began to take shape. Today, modern surveys, such as the Gaia mission chart, stars with extraordinary precision, measuring their positions and motions in 3 dimensions. Gaia has already mapped more than 1 billion stars, an astonishing achievement. And yet, even that represents less than 1% of the Milky Way's total population. The census is ongoing. Most stars remain uncounted, glowing faintly in the distant disk or hidden deep within clouds of gas and dust. One of the most striking discoveries is how unevenly stars are distributed. Near the galactic center, stars are packed tightly together, so close that from a planet there, the night sky would blaze with light. Farther out toward the edges, stars are scattered more sparsely separated by immense distances. Our sun lies somewhere in between, in a relatively calm and quiet neighborhood. From our vantage point, stars appear evenly spread across the sky. But that sense of uniformity is an illusion created by distance. In reality, stars gather in clusters, form associations, and trace the sweeping curves of spiral arms. Counting stars becomes a way of reading the galaxy's architecture. Not all stars are alike. Some are giants tens or even hundreds of times more massive than the sun. They burn fiercely and live briefly, sometimes only a few million years, before ending their lives in supernova explosions. Others are small red dwarfs, cooler and dimmer, capable of shining for trillions of years. These faint stars make up the majority of the galaxy's population, hard to see, but unimaginably numerous. They are the quiet background, the unseen majority. If you counted only the bright stars visible to the naked eye, you would be missing almost all of the Milky Way's inhabitants. To understand the galaxy's true size, astronomers must account for what cannot easily be seen. There are also stars that are not alone. More than half exist in multiple systems, pairs of suns orbiting each other, or even triples, quadruples, and more complex arrangements. Each of these stars contributes to the total. Each follows its own orbit, shaped by gravity and time. So when astronomers count stars, they are not just tallying individuals, they are counting families, networks, entire systems bound together. And when you imagine planets circling these stars, the sheer variety of possible worlds begins to unfold. In that sense, counting stars is not only about quantity, it is also about history and about possibility. The oldest stars in the Milky Way are more than 13 billion years old, nearly as ancient as the universe itself. They reside mostly in the galactic halo, gathered in globular clusters, shining faintly with chemical signatures left over from the early cosmos. Younger stars like those found in the spiral arms formed later from gas enriched by countless generations of supernova explosions. By studying how stellar ages are distributed, astronomers can reconstruct the story of how the galaxy slowly built itself over billions of years. Each star becomes a data point along a vast timeline, a quiet marker of when and where Vedder gathered and ignited. In this way, counting stars is like counting the rings of a tree, revealing the growth of something immense, layered, and ancient. Yet beyond the science, there is something deeply human in the act of counting. Children lying beneath the night sky often try it, pointing at one star, then another, until the task gently slips beyond control. There is a dreamlike quality to the attempt, as if naming or numbering the lights could somehow bring the infinite within reach. Ancient cultures traced constellations across the sky, weaving stories between the stars. Farmers watched their rising and setting to mark the seasons. Navigators followed them across dark oceans. Each point of light became more than physics. It became meaning. In that sense, counting stars was also counting connection, a shared human relationship with the sky. When you expand that thought to the scale of the galaxy, the idea grows even larger. If there are hundreds of billions of stars, and many of them host planets, how many worlds must exist? Some may be scorched and airless, others frozen and silent. Some may hold oceans' clouds or long histories of change. Perhaps a few harbor life. Perhaps somewhere intelligence looks up at its own night sky and wonders how many stars there are. Counting stars, then, is not just about quantity. It is about asking how many chances there might be for company, how many stories could be unfolding at the same time across the galaxy. Astronomers use many approaches to refine their estimates. Infrared surveys peer through dust to uncover hidden stars. Radio telescopes trace hydrogen gas, revealing regions where new stars are forming. Computer simulations model how stars live, evolve, and eventually die. Together, these methods help estimate not only how many stars exist now, but how many have existed throughout the galaxy's long lifetime. Because the Milky Way is not static, stars are constantly being born and fading away. Matter is recycled. New generations emerge from the remnants of the old. Counting stars, therefore, is never a single fixed number. It is a living process, always changing, always in motion. It's easy to forget that our own sun is one of those counted stars. To us, it feels singular, central, essential, but from the perspective of the galaxy, It is ordinary, average in size, average in brightness, unremarkable in position. And yet, from this ordinary star, extraordinary things emerged. Earth formed, life arose, consciousness developed, and now you are here listening to reflections about counting stars. That link between the ordinary and the extraordinary may be the most humbling realization of all. Some astronomers and writers compare the number of stars in the Milky Way to the number of grains of sand on all the beaches of Earth. The comparison is imperfect, but it captures a sense of scale. If every star were a grain of sand, our galaxy would be a beach stretching beyond the horizon. To stand there and try to count would be impossible. And yet, just as a beach is made of individual grains, the galaxy is made of individual suns. Each one is real. Each one bundles radiates and moves through space. The total may be unimaginable, but the parts are tangible. And so the act of counting becomes symbolic. We know we can never finish it. Still, we try. It is how humans reach toward the unknown, how we give shape to vastness. Children counting stars before sleep, astronomers tallying with billion-dollar telescopes, different scales, the same impulse. Both impulses come from the same place. To count is to connect to draw something unreachable into the quiet space of thought. And even when the numbers become overwhelming, something softer begins to form. Dreams. Each star becomes a story. Each attempt at counting opens a new possibility. Perhaps somewhere else in the galaxy, someone is doing the same thing, standing beneath a different sky, in a different spiral arm, counting points of light and wondering the same questions. Perhaps they feel the same awe, the same sense of smallness, the same pull toward understanding. The Milky Way is vast enough to hold countless lives, countless stories, countless dreams. So when we ask how many stars there are, we are really asking how wide the field of possibility might be. And in every sense, the answer slips just beyond measure. But that doesn't mean we stop trying. It means that the act of counting itself becomes part of the wonder. From inside the Milky Way, imagining its full shape is not easy. We see the glowing band stretched overhead, but we cannot step outside to view it from afar. To understand its form, astronomers rely on careful observation, mapping star positions, tracing clouds of gas, and modeling motion over vast timescales. From this patient work, a picture has slowly emerged, a spiral galaxy with sweeping arms curling outward from a bright central bulge. These arms are not rigid structures. They are regions of slightly higher density places where stars, gas, and dust gather into graceful arcs. They give the Milky Way its character and define the environment in which we travel. Our solar system resides within one of these features, not in a major arm, but in a smaller spur between two larger ones. The Sun and its planets orbit within what is known as the Orion Arm, nestled quietly between the Sagittarius Arm and the Perseus Arm. From this position, we look outward across the disk, seeing the accumulated glow of stars aligned along these vast structures. The spiral arms themselves are not solid walls of stars. They behave more like slow-moving traffic patterns, Within the galactic disk regions, where material temporarily gathers, compresses, and ignites waves of star formation, stars drift into the arms and later drift out again. But the density wave itself persists, winding gently through the galaxy. It can be misleading to imagine spiral arms as permanent objects. Instead, they are patterns like ripples across water or sound waves moving through air. The material within them is always changing, but the wave continues shaping where new stars are born. The Orion Arm, where we find ourselves, contains many familiar constellations, patterns of light that have guided stories, navigation, and imagination for thousands of years. And from this quiet location within the spiral, we continue to look outward, counting, wondering, and drifting gently through the glow. The Orion constellation itself, marked by its familiar belt of three bright stars, gives this region of the galaxy its name. Alongside Orion, this local stretch of the Milky Way includes stars from Cygnus and Perseus, parts of Scutum and Carina, and many of the nebulae visible through telescopes. When you see glowing clouds, such as the Orion Nebula or the Lagoon Nebula, you are looking directly into stellar nurseries embedded within these spiral structures. These are places where gas and dust gather, collapse, and quietly begin the long process of forming new stars. The scale of the spiral arms themselves is immense. The Perseus Arm, one of the Milky Way's major features, lies roughly 10,000 light years from our solar system and wraps around much of the galactic disk. Closer to the center lies the Sagittarius Arm, rich with star clusters and luminous nebulae. Deeper still is the Scutum Centaurus Arm, among the largest and most massive, stretching across the galaxy's inner regions. Farther out along the faint outer edge lies the outer arm, subtle, difficult to observe, yet still a real part of the spiral pattern. Each of these arms contains billions of stars, vast rivers of gas, and dust clouds spanning thousands of light years. Astronomers have identified these structures through careful mapping of radio emissions, especially those produced by hydrogen gas. Hydrogen emits radio waves at a wavelength of 21 centimeters radiation that can pass through dust clouds that block visible light. By measuring these signals and observing how their wavelengths shift due to motion, scientists can reconstruct the Milky Way's structure even from our internal vantage point. It is a little like trying to draw a map of a forest while standing among the trees. You can only see what surrounds you, but by combining countless observations from different directions, the broader pattern gradually emerges. One of the most important roles of spiral arms is their influence on star formation. As density waves move through the disk, they compress clouds of gas, triggering collapse. Massive stars form, shine intensely, and live briefly, sometimes only a few million years, before ending their lives in spectacular explosions. Because these bright stars burn out so quickly, they remain close to their birthplaces, marking the spiral arms with light. Nebulae young clusters and groups of hot blue stars trace the paths of the arms, making them visible across the galaxy. Smaller stars, like our Sun, live much longer. Over billions of years, they drift away from their birth regions and scatter throughout the disk. In this way, the spiral arms act as cradles of creation, constantly renewing the galaxy. Our own position within the Orion arm gives us a relatively calm vantage point. If we lived deep within a major arm, the sky might glow so brightly with stars that dark space would be difficult to see at all. Here on a quieter spur, we have a clearer view outward. The night sky as we know it, its constellations, patterns, and familiar landmarks, is shaped by this galactic address. It is humbling to realize that human stories, navigation, and even our sense of the cosmos are influenced by where we reside within the Milky Way. The spiral arms themselves rotate around the galaxy, but not as solid structures. Stars closer to the center orbit faster than those farther out, a phenomenon known as differential rotation. If the arms were rigid, they would wind tightly and vanish over time. Instead, the density wave model explains how the pattern persists. The arms are not made of the same stars forever. They are regions where stars continually appear and fade, much like cars entering and leaving a traffic jam while the congestion itself remains. This dynamic balance between change and stability is what makes spiral galaxies both elegant and complex. When we look at images of other galaxies, the arms appear as luminous arcs wrapping around bright centers. Galaxies like the whirlpool or the pinwheel show us what the Milky Way might look like from the outside. Their arms glow with the soft pink light of hydrogen gas energized by young stars. Dark dust lanes weave through them, absorbing light and creating contrast. The resemblance between these galaxies and our models of the Milky Way reassures astronomers that their understanding is close to the truth. Spiral arms are not unique to our galaxy. They are common features throughout the universe. Some galaxies display two grand symmetrical arms. Others show many fragmented, irregular ones. The Milky Way appears to lie somewhere in between a barred spiral galaxy. At its center stretches a bar-shaped concentration of stars extending across the bulge. This bar helps funnel gas inward, shaping the inner dynamics of the galaxy and influencing how stars continue to form. The spiral arms are not just stellar pathways, they help regulate the future of the galaxy itself, controlling how quickly gas is transformed into new generations of stars. Over billions of years, the galaxy has lived in a delicate balance. If stars formed too quickly, the available gas would be consumed and the galaxy would slowly dim. If too few stars formed, the Milky Way would fade into quiet darkness. The spiral arms help maintain that balance. They establish a steady rhythm, gathering material, triggering star birth, and allowing the process to continue across cosmic time. From our position on Earth, this spiral structure is not immediately obvious. The Milky Way appears as a luminous band because we see it edge on, looking through the thickness of the disk. The arms themselves are hidden within that glow. Only by measuring distances, motions, and subtle shifts in light have astronomers been able to reveal the spiral pattern beneath. And once you know it's there, the sky begins to look different. Each cluster, each glowing nebula, each bright region along the band becomes a quiet clue, a sign of the underlying design. The Orion Nebula, visible even without a telescope, as a faint smudge of light, is one such clue. It is a stellar nursery within our local arm, a place where the process of creation is still unfolding. The scale of the spiral arms is difficult to fully grasp. Each one stretches for thousands of light years and spans hundreds of light years in thickness. Within them, countless suns orbit, each potentially surrounded by worlds of its own. Between the arms, stellar density drops, but only by human standards. Even these quieter regions remain immense. The distinction between arm and interarm space is not absolute. Stars drift in and out over time, carrying their planets with them. The arms are not walls or borders. They are waves patterns moving through the larger disk, and yet they define our place in the galaxy. They provide the context in which our solar system travels. To think about the spiral arms is to think about connection. We are tied to the Milky Way, not only by gravity, but by the patterns that shape it. The arms gather material, stars are born. They scatter that material back into space, and the cycle repeats. We are products of that cycle. The atoms in your body were forged in earlier generations of stars. Stars that lived and died after passing through spiral arms long before the sun existed. Every breath you take, every cell you carry, is linked to these sweeping structures. And the arms do not stand still. Over the next hundreds of millions of years, our solar system will continue to drift, carried along by its orbit. It will pass through new regions, encounter new stellar neighbors, and gain new perspectives on the galaxy. The arms will keep guiding where stars form, where clusters gather, where nebulae glow. They are not static features, but living patterns enduring even as their contents change. To understand the spiral arms is to sense the heartbeat of the Milky Way, the slow rhythm by which it grows, renews itself, and evolves. When people imagine the Milky Way, they often picture the glowing band of stars arcing across the night sky. But hidden within that light lies a region that defines the galaxy itself. Deep in the direction of the constellation, Sagittarius rests the galactic center, a crowded, energetic, and mysterious region that acts as the Milky Way's core. It is not something we can see directly with our eyes. Thick clouds of gas and dust block visible light, concealing the center from ordinary telescopes. Yet through radio waves, infrared light, and X rays, astronomers have gradually peeled back those layers. What they have found is a landscape unlike any other in the galaxy. The galactic center lies about 26,000 light years from Earth. The signals we detect from it today began their journey long before human civilization existed. When those photons set out, woolly mammoths still walked the northern plains, and the last ice age was nearing its end. By the time they reached our instruments, entire chapters of human history had unfolded. So when you look toward Sagittarius on a dark night, you are not just facing a dense patch of stars. You are gazing in the direction of something ancient and powerful, a core that has shaped the Milky Way for billions of years. The central region of the Milky Way spans only a few hundred light years, yet within that small volume lies an extraordinary concentration of mass and activity. Stars there are packed far more tightly than in our quiet neighborhood. Near the core, a single cubic light year can contain hundreds, sometimes thousands of stars. If you were standing on a planet in that region, the night sky would feel entirely different. Instead of a scattered dome of distant points, the heavens would blaze with light. Countless suns would crowd the sky, many shining brightly enough to cast shadows. Familiar constellations would disappear, overwhelmed by brilliance. The sense of cosmic solitude we sometimes feel on Earth would give way to something else, a feeling of closeness, as though the universe itself pressed in from every direction. But density alone does not define the galactic center. At its heart lies the most powerful gravitational anchor in the Milky Way, a supermassive black hole known as Sagittarius, a star. With a mass of about 4 million suns, it sits quietly at the galaxy's core. Its existence was confirmed not by direct sight, but by patience. Over decades, astronomers tracked the motions of stars near the center, watching them race around an invisible point. Some completed full orbits in just a few years. Only an object with enormous gravity compressed into a tiny region could explain such motion. In 2022, humanity caught its first glimpse. The Event Horizon Telescope released an image of Sagittarius, a star, a soft blurred ring of glowing gas surrounding a dark shadow. For the first time, we saw the silhouette of the object anchoring our entire galaxy. Despite its fearsome reputation, Sagittarius, a star is surprisingly calm. Many galaxies host active black holes, quasars that unleash vast jets of energy across millions of light years. By comparison, our galactic center is quiet, almost restrained. It does flare from time to time, emitting bursts of X rays and radio waves as material drifts inward. But most of the time, it feeds gently. That calmness matters. If Sagittarius A star were as active as some of its counterparts, Earth could be bathed in radiation capable of disrupting life. Instead, we orbit far away, largely unaffected by its occasional outbursts. The surrounding region, however, is anything but peaceful. Gas clouds swirl and collide, compressed by gravity and shock waves. New stars form rapidly. The galactic center is one of the most intense star-forming environments in the Milky Way. Massive stars ignite, burn fiercely, and die young, often within a few million years. Their supernova explosions seed the region with heavy elements. Shock fronts ripple outward, triggering new collapses in nearby clouds. Creation and destruction unfold side by side, condensed into a relatively small region of space. Most of this energy is hidden from human eyes, but infrared and radio telescopes have revealed remarkable structures with almost poetic names. The Arches cluster, the quintuplet cluster, the central molecular zone. These are dense collections of stars and gas packed more tightly than almost anywhere else in the galaxy. The Arches cluster, for example, contains some of the most massive stars, known each dozens of times heavier than the Sun, all confined within just a few light years. Their radiation and powerful stellar winds carve cavities in surrounding gas, sculpting the environment into chaotic, ever changing shapes. To us, these are faint signals translated into data, but to an observer near the core, the spectacle would be overwhelming. What makes the galactic center even more remarkable is how deeply it connects to the rest of the Milky Way. The spiral arms converge toward it like spokes meeting a hub. A bar shaped structure of stars stretches across the central bulge, channeling gas inward, feeding both star formation and the black hole itself. The behavior of the entire galaxy depends on this inner engine. The motion of stars in the disk, the orbits of satellite galaxies, the shape and persistence of spiral arms, all are influenced by the mass concentrated at the center. It is the hidden heartbeat of the Milky Way, steady, powerful, and persistent. And though distant, the core has played a role in Earth's story as well. As our solar system completes its long orbit around the galaxy, once every few 100 million years, it passes through changing regions, environments, and conditions. Those journeys continue quietly, far beyond the scale of a single lifetime. Some scientists have suggested that as our solar system drifts through denser regions of the spiral arms or passes closer to the galactic center, subtle effects may ripple outward. The influx of cosmic rays could change slightly. Distant comets in the outer reaches of the solar system might be nudged from their long, quiet orbits. Whether these effects directly influence life on Earth is still debated, but the idea itself reveals something important. Our lives are deeply woven into the larger motions of the galaxy. Even here, far from the core, we are never truly separate from its pull. The black hole at the center remains one of astronomy's great enigmas. We know its mass, we know its location, yet fundamental questions remain. How did it form? Did it begin as a smaller black hole in the early Milky Way, gradually growing by drawing in gas and stars? Or was it born already massive, seeded by the collapse of enormous primordial clouds shortly after the universe began? The answers may reveal how galaxies themselves grow and evolve. Nearly every large galaxy appears to host a central black hole, and the close relationship between a galaxy's size and the mass of its black hole suggests a deep connection, as if the heart and the body develop together. Closer to home, astronomers continue to observe Sagittarius, a star, with ever more refined instruments. Infrared telescopes trace the paths of individual stars, watching them race around the unseen center at speeds of thousands of kilometers per second. Radio arrays, such as the Event Horizon Telescope, capture the faint glow of superheated gas swirling near the edge of the event horizon. Future observatories may even detect subtle gravitational waves produced by interactions near the core. With each observation, another layer is gently peeled away, revealing more of the galaxy's hidden heartbeat. For most of human history, the galactic center remained invisible, concealed behind thick lanes of dust. Only within the last century have we developed the tools to sense it indirectly. That long concealment gives the center a special quality, as if the Milky Way keeps its heart veiled, allowing only fleeting glimpses through carefully tuned instruments. And yet its presence is undeniable. The motions of stars confirm it. Bursts of energy betray it. Models of galactic structure all point inward. The center is real, powerful and constant whether or not we can see it directly. Thinking about the galactic center can stretch the mind. We live tens of thousands of light years away, circling quietly within the disk, and yet our fate is bound to it. The sun follows its orbit because of the mass concentrated there. The spiral arms persist under its influence. The history of star formation, the cycling of gas, even the existence of planets like Earth can be traced back to processes rooted in the core. It is not merely a point in the sky. It is the axis around which our galactic life turns. And although our eyes cannot see it, we can still connect to it. On a clear night, look toward the southern sky where Sagittarius rises. Imagine beyond the dust and glow, past the crowded star fields, into the hidden center. There, compressed into a relatively small region, lie the black hole dense clusters and churning clouds of gas, all shaping the galaxy on the largest scales. You may not perceive the heartbeat directly, but you are living within its rhythm. Every orbit, every rotation, every passing moment is subtly guided by its gravity. When astronomers first proposed that something extraordinary lay at the heart of the Milky Way, the idea seemed almost too strange to accept. A black hole, an object so dense that not even light could escape, sounded more like speculation than reality. But decades of careful observation slowly changed that view. The evidence became overwhelming. At the center of our galaxy lies a supermassive black hole known as Sagittarius A star, an invisible anchor with a mass equivalent to about 4 million suns. What does it mean to say there is a black hole at the center of the Milky Way? It means that billions of stars, vast clouds of gas, and entire spiral arms all move in response to an unseen concentration of gravity. We cannot observe the black hole directly in visible light. By definition, it emits none. The boundary surrounding it, the event horizon, marks the point beyond which escape is impossible. Any light that crosses that boundary is lost forever, trapped by gravity. Yet its presence is written clearly in motion. Nearby stars trace tight, fast orbits around an invisible point. Some complete full circuits in just a few years. From these silent paths, the nature of the hidden center reveals itself, slowly, patiently, through gravity alone. Only an object with extraordinary mass could account for motions like these. The realization that such an object existed at the center of the Milky Way did not come from a single moment, but from years of careful, patient work. Teams of astronomers in Europe and the United States spent decades tracking the positions of stars near the galactic center. Using infrared telescopes capable of seeing through thick curtains of dust, they followed stars, tracing tight, elegant ellipses around an unseen focus. One star, known as S2, became especially important. It completes a full orbit in just 16 years, passing astonishingly close in cosmic terms to the invisible center. By measuring its speed and path, scientists could calculate the mass of whatever it was orbiting. The result was unmistakable. Millions of suns compressed into a region smaller than our solar system. In 2020, this work was recognized with the Nobel Prize in Physics, awarded to Reinhard Genzel and Andrea Ghez for their pioneering studies of stellar orbits around the galactic center. Their persistence transformed what had once been theory into measured reality. Then in 2022, humanity took another step. The Event Horizon Telescope collaboration released the first direct image of Sagittarius A star. By linking radio telescopes across the Earth into a single planet sized instrument, the team achieved unprecedented resolution. The image itself was soft and blurred, but unmistakable. A glowing ring of hot gas distorted by extreme gravity surrounding a dark central shadow. That shadow marked the event horizon of the Milky Way's black hole. For the first time, we had captured a glimpse of the very edge of nothingness at the heart of our own galaxy, despite its immense mass. Sagittarius. A star is quiet by cosmic standards. Many galaxies host black holes that blaze with energy, consuming vast streams of gas and shining as quasars visible across billions of light years. By comparison, our central black hole is underfed. Only small amounts of matter fall inward, producing occasional flares of X rays or radio bursts. For life on Earth, this calm is a gift. A highly active quasar at the galaxy's center would flood the Milky Way with intense radiation, making conditions far less hospitable. Instead, Sagittarius, a star, remains largely dormant, a giant waiting rather than raging. But what actually happens near a black hole? Around Sagittarius, a star hot gas forms a swirling accretion disk. As this gas spirals, inward friction and compression heat it to millions of degrees, causing it to glow in X rays and radio waves. These signals are what instruments detect, not the black hole itself, but the luminous material poised on the brink of disappearance. From time to time, twisted magnetic fields snap and reconnect near the disk, producing brief but powerful flares. Astronomers have observed Sagittarius. A star brightens suddenly for hours only to settle back into quiet again. To grasp how extreme a black hole truly is, imagine compressing the sun into a sphere just a few kilometers across. That is the level of density involved. In the case of Sagittarius, a star 4 million suns are crushed into a region smaller than the orbit of Mercury. The escape velocity there exceeds the speed of light, which is why nothing, not even light, can escape once it crosses the event horizon. Space and time themselves curve inward. Distance and duration lose their familiar meaning. General relativity describes these conditions with elegant equations, but the human mind struggles to picture them. A black hole is less like an object and more like a tear in the fabric of reality, a place where the rules we know reach their limits. For much of the 20th century, black holes were treated as mathematical curiosities. Even Einstein, whose equations predicted them, doubted they could exist in nature. That changed with the discovery of X-ray binary systems, where visible stars orbit unseen massive companions. Then came mounting evidence of supermassive black holes at the centers of galaxies. Today, we know that nearly every large galaxy hosts one. Their masses scale with their galaxies in ways not yet fully understood. Galaxies and black holes appear to grow together, their histories intertwined. In that sense, Sagittarius, a star, is not an anomaly. It is a defining feature of what it means to be a galaxy. And at the heart of our own Milky Way, it continues its quiet work, shaping motion, guiding structure, and anchoring everything that slowly turns around it. The idea that the entire Milky Way revolves around a black hole can sound unsettling at first, but from where we are, its influence is gentle. The Sun does not orbit Sagittarius, a star, alone. It moves within the combined gravitational pull of billions of stars and vast amounts of dark matter spread throughout the galactic disk. The black hole dominates gravity only in the innermost few light years. Beyond that, it becomes just one component of a much larger gravitational landscape. If the black hole were to vanish tomorrow, the Milky Way would barely notice. Stars would continue their paths, guided by the distributed mass of the galaxy. Its role is critical at the core, but on the scale of the whole galaxy, it is one presence among many. And yet symbolically, it carries great weight. A black hole at the heart of our galaxy is both literal and metaphorical, a dark anchor around which everything else turns. It reminds us that the cosmos is not only stars and planets, not only nebulae and clusters, but also silent regions where matter and light disappear. Living in a galaxy shaped by such an object connects us to the broader universe. Black holes are common. They are woven into the evolution of galaxies across billions of years. The science of Sagittarius. A star is still unfolding. Astronomers continue refining measurements of its spin, its feeding behavior, and its subtle interactions with nearby stars. One enduring mystery is why it shines so faintly compared to theoretical predictions. Perhaps stellar winds blow material away before it can fall inward. Perhaps magnetic fields redirect gas outward. Understanding this quietness may unlock deeper insights into how black holes truly behave. Another area of study lies closer to the core itself. There may be dozens or even thousands of smaller black holes orbiting in that crowded region. They are remnants of massive stars slowly spiraling inward over immense spans of time. Their interactions could one day produce ripples in space-time, gravitational waves detectable by future observatories. Beyond science, the image of a black hole at the galactic center resonates on a more human level. Across history, cultures have imagined cosmic hearts, sacred fires, divine centers. Now we know that at the center of our galaxy lies something unseen, something that cannot be observed directly, yet whose presence is undeniable. A place where time slows, where light cannot escape, where the familiar rules of the universe begin to soften. For all our equations and instruments, mystery remains at the core. And perhaps that mystery is part of its power, drawing our curiosity just as gravity draws stars. On quiet nights, when you look toward Sagittarius, you can pause with this thought. Beyond the glowing star fields, beyond the dust-laced clouds, there rests this hidden giant. Its heartbeat is not audible, its form is not visible, and yet the galaxy moves in rhythm with it. Every orbit of the sun, every slow sweep of the spiral arms, every chapter in the history of star formation is in some way tied to its existence. It is silent, central, invisible to the eye, yet essential to the whole. And while we may never travel there, never send a probe across those tens of thousands of light years to approach its horizon, we can still connect to it through understanding. Simply knowing that such a place exists, that we live in a galaxy shaped by it, can gently shift perspective. It reminds us how vast the universe truly is, how strange its contents can be, and how much still waits to be discovered. The black hole at the center of the Milky Way is not only an object of scientific study, it is part of the larger story of where we live, part of the quiet background to our lives, part of the greater context of being. When most people picture a galaxy, they imagine stars first. Billions upon billions of glowing points scattered along spiral arms forming a luminous river across the night sky. But the Milky Way is not made of stars alone. Between those points of light lies an enormous amount of material that does not shine the way stars do matter, that fills the spaces between suns, shaping the galaxy in subtle but essential ways. The galaxy is threaded with vast clouds of gas, fine grains of dust, and faint glows that give structure and texture to what might otherwise seem like empty space. These hidden components are easy to overlook when we imagine the universe as stars scattered across darkness. Yet without them, the Milky Way would be unrecognizable, and life itself could never have emerged. Most of the gas that fills the galaxy is hydrogen, the simplest and most abundant element in the universe. It drifts between stars in immense clouds, sometimes spread thin across hundreds of light years, sometimes gathered into dense, massive complexes. Helium follows along with trace amounts of heavier elements, carbon, oxygen, iron forged long ago in earlier generations of stars. These clouds are the raw material of creation. Over time, gravity gathers pockets of gas, drawing them inward. As they collapse, they heat compress and eventually ignite nuclear fusion. A new star is born. In this way, the galaxy is constantly renewing itself, transforming diffuse clouds into stars, and later returning material back into space through stellar winds and supernova explosions. Dust, though far less abundant than gas, plays an equally vital role. The word dust might suggest something ordinary, the fine layer wiped from a shelf. But cosmic dust is something very different. These are microscopic solid grains smaller than a micrometer, composed of carbon silicates and metals such as iron or nickel. They are forged in the outer layers of aging stars and scattered into space when those stars shed their material or explode. Once released dust grains drift through the interstellar medium, absorbing and scattering light. To our eyes, they appear as dark lanes crossing the Milky Way, interrupting its glow. If you have ever noticed places where the luminous band of the galaxy looks streaked torn or broken, you have seen dust at work. Far from being an obstacle, this dust is essential. It shields delicate molecules from harsh ultraviolet radiation, allowing complex chemistry to unfold inside cold clouds. It provides surfaces where atoms can gather bond and form new compounds. In these quiet, hidden regions, protected by dust and cooled by distance, the building blocks of planets' oceans, and eventually life itself begin to assemble. Without dust, the birth of stars and planets would unfold very differently, perhaps not at all. Our own solar system, including Earth itself, formed from material enriched by dust, created in ancient stars. The iron in your blood, the calcium in your bones, the silicon inside your technology, all of it once passed through cycles of starlight collapse and dust. Gas and dust together give rise to many of the galaxy's most beautiful sights. When young stars ignite, their intense radiation energizes the surrounding hydrogen gas, causing it to glow in deep reds and soft pinks. These glowing regions are known as emission nebulae. The Orion Nebula, visible even without a telescope, is one such place, a cradle of new suns wrapped in luminous gas. Reflection nebulae tell a different story. They shine with a pale bluish light as dust grains scatter starlight, much like Earth's atmosphere scatters sunlight to create a blue sky. Then there are dark nebulae clouds so dense with dust that they block all light behind them. Against the star filled background, they appear as empty voids. To the eye, they look like absence, but within them, stars may be quietly forming, hidden and waiting. Radio and infrared telescopes have revealed even more of this unseen world. They have uncovered giant molecular clouds drifting through the spiral arms, some stretching hundreds of light years across. By astronomical standards, these clouds are cold only a few dozen degrees above absolute zero. Yet they are rich with possibility. Within them, scientists have detected molecules such as carbon monoxide, ammonia, and even complex organic compounds. These clouds act as the galaxy's chemical laboratories, assembling the ingredients that one day become planets and perhaps life. Observing in radio wavelengths allows astronomers to trace these clouds even when they are completely invisible in visible light. The space between stars is far from uniform. Some regions are quiet and sparse, marked only by faint traces of gas. Others are crowded with glowing nebulae dense clusters and filamentary structures woven through space. Supernova explosions send shock waves racing through the interstellar medium, compressing nearby clouds and triggering new rounds of star formation. Stellar winds carve enormous bubbles, hollowing out cavities filled with hot plasma. The result is a shifting patchwork, structures forming, dispersing, and reforming over millions of years. If you could watch the Milky Way and fast forward, you would see clouds collide, collapse, and drift apart in a slow, endless dance. Closer to home, our own sun shapes its surroundings as well. Encasing the solar system is the heliosphere, a vast bubble carved out by the solar wind. Beyond it lies the interstellar gas of our local neighborhood, sometimes called the local interstellar cloud. The sun and its planets are currently moving through this cloud, traveling at tens of kilometers per second relative to the surrounding gas. It's a quiet reminder that we are not drifting through empty space. We are moving through a medium, thin, delicate, yet real. Dust and gas also shape how we perceive the Milky Way itself. Large portions of the galaxy's far side are hidden behind thick clouds blocking visible light. For centuries, this made it difficult to understand the galaxy's true structure. Only by observing in radio and infrared wavelengths which can pass through dust, did astronomers begin to piece together the spiral arms and central bar. In this sense, we see only part of our galaxy directly. The rest must be inferred, reconstructed, and imagined through careful observation. That limitation is part of the mystery, a reminder that our perspective is always incomplete. Even though dust and gas are nearly invisible to the naked eye, they account for roughly 10 to 15% of the Milky Way's luminous matter. That may sound small, but on a galactic scale, it represents tens of billions of solar masses, enough material to form countless future generations of stars. Without this reservoir, the galaxy would slowly grow quiet. Stars would age, fade, and vanish with no replacements. With it, the Milky Way remains alive continually, creating, recycling, and renewing itself. Dust also shapes beauty in subtle ways. The reddish tint of distant stars often comes from dust scattering shorter wavelengths of light, allowing longer, redder wavelengths to pass through. This effect, known as interstellar reddening, gently alters the colors we see. Even in the darkness, dust leaves its signature, quietly painting the galaxy with softness and depth. Photographs of the Milky Way often reveal delicate networks of dark filaments, twisted and shaped by magnetic fields and slow turbulence. These patterns are not accidental. They are signatures of hidden forces, quiet currents, guiding how gas moves and how stars come into being. When you look closely at these images, it becomes clear that the Milky Way is not simply a scatter of lights on a black background. It is a textured system alive with structure at every scale. Perhaps the most humbling realization is this: everything we are emerges from that ongoing cycle. The carbon inside your cells, once drifted as interstellar gas, was fused in stellar cores, scattered by explosions, and gathered again. The oxygen you breathe was forged in ancient suns and released when those stars reached the ends of their lives. Even elements like gold, found in jewelry or electronics, were created in rare violent events, such as collisions between neutron stars. The dust and gas between the stars are not scenery, they are the source of everything tangible. To look at a glowing nebula or a dark cloud is to look at material that will one day become planets and perhaps life. Astronomers continue to study these components with ever increasing precision. Infrared observatories such as Herschel and Spitzer mapped the faint glow of cold dust, revealing clouds invisible in visible light. More recently, the James Webb Space Telescope has captured breathtaking views of star-forming regions, showing pillars and filaments of gas and dust in extraordinary detail. Each new observation adds depth to our understanding how the galaxy recycles matter, how it sustains its slow rhythm of birth and decay. Yet even without images, the idea alone is enough to stretch the imagination. It's tempting to think of the galaxy as mostly empty space, but in truth, no region is ever truly empty. Even in the most rarefied areas, a few particles drift through each cubic centimeter. Over vast distances, even this thin presence matters. It carries energy, supports magnetic fields, and subtly influences the motion of stars and cosmic rays. The Milky Way is a connected web with dust and gas forming its unseen threads. So when you look up and notice that pale band crossing the night sky, remember you are seeing only part of the story. Hidden within that glow are clouds and filaments, forming and dispersing, brightening and darkening over time. Starlight itself is shaped by what lies between stars, filtered and softened by dust and gas. The galaxy is not a static picture. It is layered, dynamic, and evolving. Every star you see, every dark lane you notice, is part of that ongoing cycle. And within that cycle, you have a place. The atoms in your body, the water you drink, the ground beneath your feet, were once dust and gas drifting between the stars. You are living evidence of the galaxy's hidden processes. To understand interstellar dust and gas is, in a very real sense, to understand your own origins. The glow between the stars is not distant or irrelevant. It is intimate, woven into your being, connecting you to the Milky Way in the most literal way. When people first began to wonder about the size of the Milky Way, the challenge must have felt impossible. How do you measure something you cannot step outside of? You can walk around a tree, climb a mountain, map a continent. But when you live inside the very structure you want to understand, there is no simple vantage point. The galaxy surrounds us in every direction so vast that no single glance can reveal its form. For centuries, it was a question without an answer, a riddle that seemed destined to remain unresolved. And yet, through patience, careful observation, and a willingness to think far beyond ordinary scales, ways forward slowly emerged. Early astronomers tried a simple approach, counting stars. In the late 1700s, William Herschel conducted systematic surveys, pointing his telescope toward different regions of the sky and recording how many stars appeared in each direction. His reasoning was straightforward. If more stars were visible in one direction, the galaxy must extend farther that way. Fewer stars would suggest a shorter reach. From this method, Herschel concluded that the Milky Way had the shape of a flattened disk and that the Sun lay near its center. It was an imperfect picture, but it was a beginning. Although limited by the technology of his era and by the obscuring veil of interstellar dust, William Herschel's work marked one of the earliest attempts to turn an infinite-looking sky into something measurable. It was an imperfect beginning, but a bold one. As time passed, new tools opened new windows. Photography allowed astronomers to capture faint stars invisible to the naked eye, extending vision far beyond human limits. Spectroscopy added another dimension, revealing the temperatures, chemical compositions, and motions of stars through their light. With each advance, stars once thought distant were revealed to be far farther still. The scale of the Milky Way continued to grow, and with it our sense of awe. One of the most transformative breakthroughs arrived in the early 20th century. At the Harvard College Observatory, Henrietta Leavitt discovered a remarkable relationship in a class of stars known as Cepheid variables. These stars pulse rhythmically, brightening and dimming over regular periods. Leavitt found that the length of a Cepheid's pulse was directly linked to its true brightness. This insight changed everything. By comparing how bright a Cepheid appears from Earth to how bright it truly is, astronomers could calculate its distance. For the first time, the universe had a reliable measuring stick. With it, scientists began mapping the structure of the Milky Way with far greater accuracy, and soon after they proved that other galaxies existed beyond our own. Even so, measuring the full size of the Milky Way remained a challenge. Light from distant stars is dimmed and reddened by interstellar dust, making them harder to detect. And the sheer scale of the disk means that even the brightest objects can fade into invisibility before their light reaches us. Another approach was needed. That approach came through radio astronomy. Hydrogen, the most abundant element in the galaxy, emits radio waves at a wavelength of 21 centimeters. Unlike visible light, these waves pass easily through dust clouds. By mapping this emission across the sky and measuring its motion through the Doppler effect, astronomers traced the spiral structure of the Milky Way from the inside. What had been hidden suddenly took shape. The galaxy's arms emerged clearly on maps winding through space. In more recent decades, technology has advanced even further. The Gaia spacecraft, launched by the European Space Agency, is measuring the positions and motions of more than 1 billion stars with extraordinary precision. By detecting tiny shifts in apparent position, parallax as Earth orbits the Sun, Gaia provides direct distances to stars thousands of light years away. The result is the most detailed three-dimensional map of the Milky Way ever created. With each update, our picture sharpens. The true shapes of spiral arms, the tilt of the disk, the clustering of stars, all emerge with increasing clarity. And yet, even now, the question remains: how big is the galaxy? There is no single answer. If we measure only the bright disk, where most stars reside, the Milky Way spans roughly 100,000 light years. If we include the sparse halo of stars and globular clusters, the diameter grows to several 100,000 light years. If we account for the dark matter halo, which outweighs all visible matter, the galaxy's gravitational reach may extend into nearly 1 million light years. Each definition describes a different layer. Each is correct in its own way. Measuring the Milky Way is not about finding one number. It is about understanding structure upon structure. Even the units themselves resist intuition. A single light year is nearly 10 trillion kilometers. When we say the galaxy is 100,000 light years across, we are speaking of distances so vast that everyday metaphors collapse. Even the fastest spacecraft humanity has ever built would take millions of years to cross it. So astronomers turn to scaling analogies. If the Milky Way were shrunk to the size of North America, our entire solar system would fit inside a coffee cup. If the galaxy were the size of a dinner plate, the distance between the Sun and Pluto would be thinner than a human hair. These comparisons are imperfect, but they offer a hint of how unmeasurable the unmeasurable feels. Another way to understand the galaxy is through its mass. By tracking how stars and gas move, astronomers calculate the total gravitational pull holding everything together. The result is staggering. The Milky Way contains the equivalent of 1 to 2 trillion suns in mass, and most of that mass is invisible. Stars, nebulae, and dust account for only a small fraction. The rest exists as dark matter, unseen, undetectable, directly yet unmistakable in its effects. Measuring the galaxy, then, means grappling with what cannot be seen, with something revealed only through its influence. Globular clusters provide another guide. These dense spheres of ancient stars orbit far from the galactic center, tracing the outer halo. By studying their positions and motions, astronomers map the edges of the Milky Way's gravitational reach. Piece by piece, layer by layer, the impossible begins to take shape. Each globular cluster is like a quiet lantern suspended in the dark, glowing from the outskirts of the Milky Way and helping outline the reach of our galactic home. And yet, even with all these tools, uncertainty remains. Depending on the methods used and the definitions chosen, measurements can differ by tens of thousands of light years. The galaxy is not a cleanly bounded object. It is a diffuse, evolving system. Stars slowly drift outward. Smaller galaxies are drawn inward and merge. Streams of gas stretch across an intergalactic space, blurring the edges. To measure the Milky Way is to measure something in motion, a target that subtly shifts as we try to define it. This makes the task both a scientific challenge and a philosophical reminder. Some things resist precise borders. Some structures do not end sharply, but fade gradually into something else. Still, the progress humanity has made is extraordinary. From Herschel's early star counts to Gaia's catalog of more than 1 billion stars, our reach has expanded across scales once thought impossible. With every advance, more detail appears, more structure, more nuance. We measure the unmeasurable, not by forcing it into simplicity, but by learning to work with complexity. The galaxy is not a single number. It is a tapestry of dimensions, diameter and thickness, mass and luminosity, age and motion. Together, these pieces form a picture that is never complete, yet always improving. There is also a personal side to all this measuring. Every number we calculate, every map we draw, helps place us within the cosmos. To know the Milky Way spans about 100,000 light years is to recognize that our lives unfold in a tiny corner of something immense. To know it contains trillions of solar masses is to understand how small our planet truly is within a vast gravitational system. Measurement, even when imperfect, grounds awe and understanding. It turns wonder into knowledge without diminishing the wonder itself. And yet, despite all this progress, mystery remains. The farther out we look, the harder the galaxy becomes to define. The halo thins into intergalactic space, merging almost imperceptibly with the domains of neighboring galaxies. There is no clear line where the Milky Way ends and something else begins. To measure the unmeasurable is to accept ambiguity, to recognize that boundaries are often human ideas imposed on a universe that does not follow neat divisions. Still, the attempt matters. Each new survey, each refined model brings the galaxy a little closer to comprehension. Not complete understanding, perhaps never that, but enough to tell a coherent story, enough to know where we are, how we fit, and what surrounds us. The Milky Way may be staggering in size, but it is also knowable in degrees, measurable step by step, approachable through patience. The unmeasurable becomes measurable not by shrinking it, but by expanding ourselves. So when you think about the size of the Milky Way, you might imagine astronomers leaning quietly over telescopes, watching stars drift across sensitive detectors. You might picture satellites scanning the sky with steady, unblinking eyes, or computers sifting through oceans of data, tracing spiral arms and faint halos. Each act of measurement is a thread. Together, they weave an image of something too large to see all at once. That image is still unfinished, still growing, and within it, we find ourselves living inside a galaxy that is at once measured and immeasurable, known and unknowable, vast beyond comprehension, yet slowly, patiently understood. When we begin to talk about the true scale of the galaxy, the units of everyday life quickly lose their meaning. Kilometers and miles work well for roads and flights, but when stretched to cosmic distances, they collapse into absurdity. Even astronomical units, the distance from Earth to the Sun, become unwieldy once we move beyond the boundaries of the solar system. Astronomy needed a different kind of ruler, one designed for immensity, a way to describe distances so vast that ordinary numbers would otherwise overwhelm us. That ruler is the light year. Despite its name, a light year is not a unit of time. It is a measure of distance, the span light travels in a single year, and it has become the gentle tool by which we navigate the universe. Light is the fastest thing we know, moving at roughly 300,000 kilometers per second. In the time it takes to blink a beam of light, could circle Earth several times. Stretched across an entire year, that speed carries light nearly 10 trillion kilometers. That distance, unimaginably large by human standards, is one light year. To put it another way, a car driving non-stop at highway speed would need more than 10 million years to cross just a single light year. Even Voyager 1, humanity's farthest traveler, has covered only a tiny fraction of that distance, despite racing outward for decades. And yet, when astronomers speak of galaxies, they casually refer to tens of thousands or hundreds of thousands of light years as if they were ordinary figures. This is the quiet brilliance of the light year. It transforms distances beyond imagination into numbers we can work with. When we say the nearest star system is about 4 light years away, the number feels large but manageable. 4 steps on a ruler made of light. When we say the Milky Way's disk spans roughly 100,000 light years, the scale fits the unit even if the reality remains staggering. The light year is a gentle ruler, not because the distances are small, but because the language becomes usable. It gives us a way to speak about what would otherwise remain unspeakable. There is also something quietly poetic hidden in the idea. Because light takes time to travel measuring distance, in light years also means measuring history. To say an object is 10,000 light years away is to say we are seeing it as it was 10,000 years ago. Distance and time merge into a single concept. The Milky Way is not only wide in space, it is deep in time. Every star we see is also a message from the past. Its light has crossed immense gulfs before reaching our eyes, carrying with it a fragment of history. The light year measures not just separation, but memory. This need for such a unit emerged naturally as astronomy became more precise. Early observers could map positions and motions, but distances remained elusive. Without knowing how far away stars truly were, the scale of the universe was little more than educated guesswork. The first reliable method came through parallax, the tiny apparent shift of a nearby star against the distant background as Earth moves around the Sun. These shifts are minuscule, often less than a fraction of an arcsecond, but with careful instruments, they reveal distances measured in light years. Nearby stars show detectable parallax. More distant ones require indirect methods. Cepheid variables and other standard candles, stepping the scale outward layer by layer. The light year became the natural language for expressing these results. Even today, astronomers often use another unit, the parsec, which equals about 3.26 light years. Professionals favor it for technical work, but for most people, the light year remains more intuitive. It connects directly to the speed of light, something almost everyone has heard of. You can say a star is 10 years of light travel away, and even if the distance is vast, the meaning feels tangible. Within the Milky Way, light years define every structure. The nearest stars lie a few light years away. Spiral arms span thousands. The main disk stretches across 100,000. The halo reaches hundreds of thousands more. When astronomers describe the galaxy's thickness, they say the thin disk is about 1,000 light years deep. These numbers make sense because they share the same language. Without the light year, the Milky Way would dissolve into endless strings of zeros, alienating, abstract, and impossible to hold in the mind. With it, the galaxy becomes vast, but describable, distant, but imaginable. With the light year, we can speak calmly about distances that completely escape everyday experience. And yet, for all its usefulness, this unit humbles us. Knowing that even the nearest stars are years away at the fastest possible speed reminds us how isolated we truly are. Any message sent to a hypothetical neighbor would take decades to arrive. Journeys to even the closest star systems remain far beyond our present reach. The light year ruler shows us not only how vast the galaxy is, but how limited our physical reach still remains. It is a gentle ruler, but also a firm one, quietly reminding us of boundaries we cannot yet cross. Still, there is comfort in its constancy. The speed of light is a universal constant, the same everywhere, unaffected by motion or circumstance. That makes the light year a dependable measure, one that holds true no matter where you are in the galaxy. In a universe filled with complexity and change, that reliability is a gift. It allows us to measure, to compare, and to communicate across distances that would otherwise remain meaningless. The light year also reveals something subtle about our place in the cosmos. When we look out at the Milky Way, we are not seeing it as it exists now, but as it existed across a range of times. Stars 1,000 light years away appear as they were 1,000 years ago. The galactic center, 26,000 light years distant, is seen as it was when humanity was just beginning to shape tools. The far side of the galaxy shows us an era that predates our species entirely. In this sense, the Milky Way is a time machine as much as it is a structure in space. The light year measures not only where something is, but when we are seeing it. Astronomers use light years not just to describe distance, but to frame motion and energy. Supernova remnants are traced by light echoes expanding across light years. Star clusters are defined by their spread over light years. Even the most distant cosmic explosions are studied by how their light travels through light years to reach us. The unit has become more than a convenience. It is woven into the language of astronomy itself, the natural way we describe the universe. For the Milky Way light years form a quiet map of home. The Sun orbits about 26,000 light years from the center. Spiral arms stretch for thousands. Globular clusters roam hundreds of thousands of light years away. Expressed in light years, these scales become thinkable. We may never cross them physically, but we can cross them with thought, stepping from one light year to the next in imagination. And yet the light year remains abstract until you pause and reflect on what it truly means. Imagine a beam of light leaving a distant star. Photons stream outward in all directions, traveling for years, decades, millennia. Some pass through dust clouds, some slip between stars. A few eventually strike the back of your eye as you gaze into the night. In that moment, you are receiving the end of a journey measured in light years. The ruler is no longer just scientific, it becomes intimate. Each star you see is a message delivered across vast stretches of space and time, arriving precisely in your moment of awareness. The light year earns its name as a gentle ruler because it lets us approach immensity without being overwhelmed. The galaxy could be described in kilometers, but the numbers would dissolve into meaninglessness. The light year rescales the impossible into something the human mind can begin to hold. It allows us to measure without despair, to explore without fear. It bridges the gap between our brief lives and the enormous universe around us. So when you hear that the Milky Way is 100,000 light years across, let the number linger. Imagine light itself, the fastest thing that exists, racing for a century just across 100 light years, then repeating that journey 1,000 times to span the galactic disk. Picture those beams threading through dust, weaving among stars, carrying silent records of the galaxy's shape. Each light year is distance and story and memory, and together that they measure not only the size of the Milky Way, but our place within its slow, patient rhythm. When you step outside on a clear night and look up, the Milky Way appears as a soft, luminous band stretching from one horizon to the other. From that simple view, it is easy to imagine it as a flat ribbon, a straight path drawn across the sky. But the true shape of our galaxy is far more intricate. Uncovering that shape has been one of astronomy's greatest challenges, largely because we are not observers standing at a distance. We live inside the Milky Way itself. Trying to understand its form is like trying to map an entire forest while standing among the trees. We see trunks, branches, and clearings, but never the whole outline at once. And yet, through patience and imagination, astronomers have slowly assembled a picture. One of the earliest clues came from a simple observation: the stars of the Milky Way are not scattered evenly across the sky. They cluster along a narrow band. That band marks the plane of the galactic disk, the region where most of the galaxy's stars, gas, and dust reside. In the 18th century, William Herschel attempted to chart this distribution by counting stars in different directions. His methods were limited, and dust obscured much of what lay beyond. Still, his conclusion captured the essence of the truth. The Milky Way is shaped like a flattened disk. This disk spans tens of thousands of light years across, yet is only about 1,000 light years thick in the region where most stars are found. It is vast in width, but remarkably thin. As technology advanced, new details emerged. Observations in radio and infrared light able to pass through dust revealed that the disk is threaded with spiral arms. Our galaxy is not a smooth plate, but a barred spiral. At its center stretches an elongated bar of stars, crossing the bulge like a luminous bridge. From this bar spiral, arms curve outward, wrapping around the galaxy in slow, graceful arcs. Our solar system lies within one of the smaller structures, a local spur between two major arms, about 26,000 light years from the galactic center. The central bulge is another defining feature. It is a dense, football shaped concentration of older stars surrounding the supermassive black hole at the heart of the galaxy. The bulge blends smoothly into the central bar, forming a crowded and energetic region very different from our quieter surroundings. From Earth, this bulge reveals itself as a bright thickening of the Milky Way's band in the direction of Sagittarius, where the light of countless overlapping stars merges into a glowing core. Beyond the disk and bulge lies the halo. This is a vast, roughly spherical region extending hundreds of thousands of light years in every direction. It contains sparse stars, ancient globular clusters, and most importantly, dark matter. The halo is faint and difficult to observe, yet it plays a crucial role. It holds much of the galaxy's mass and provides the gravitational glue that keeps the disk and spiral arms intact. Without the halo, the Milky Way would not remain bound. Its stars would drift apart into space. Within the halo are some of the oldest stars in the galaxy, relics from its earliest days, along with long streams of stars left behind by smaller galaxies that were torn apart and absorbed over billions of years. Another surprising discovery is that the Milky Way's disk is not perfectly flat. Instead, it is warped and twisted, bending gently up and down like a vinyl record left too long in the sun. The outer regions curve into a subtle S shape. This warp may be caused by gravitational interactions with nearby satellite galaxies, such as the Magellanic Clouds, or by uneven distributions of dark matter pulling on the disk. Whatever its origin, the warp reveals something essential. The Milky Way is not rigid or static. It is dynamic, responsive, and constantly shaped by its surroundings. Its form continues to evolve, influenced by mergers, tidal streams, and the slow pull of gravity over immense spans of time. And hidden within these structures, disk, bulge, halo, and arms are the clues to how our galaxy formed how it grew, and how it continues to change. Faint streams of stars arc silently through the darkness, long trails that mark the paths of ancient encounters. They are the lingering signatures of collisions long past. One such example is the Sagittarius dwarf galaxy, which is even now being pulled apart. Its stars have been stretched into an immense ribbon wrapping around the Milky Way like a cosmic thread. These stellar streams blur the galaxy's edges, reminding us that its shape is not a clean outline, but a layered history written by mergers and change. The form of the Milky Way also reveals itself through motion. By measuring how fast stars orbit at different distances from the center, astronomers construct what is known as a rotation curve. If only visible matter were present, stars farther out would move more slowly. But that is not what we observe. Instead, orbital speeds remain nearly constant far into the outskirts of the galaxy. This quiet persistence is one of the strongest pieces of evidence for dark matter and invisible presence surrounding the Milky Way, shaping its structure through gravity. Without dark matter, the spiral arms would slowly unravel. With it, the galaxy holds together in a vast, unseen embrace. Comparisons with other galaxies offer further insight. When we observe spiral systems such as Andromeda or the Whirlpool Galaxy, familiar patterns emerge: central bulges, sweeping arms, extended halos. The Milky Way appears to share this same general design, even if each galaxy has its own character. Studying these neighbors is like examining nearby houses to infer the shape of your own roof hidden from view because you stand beneath it. Despite decades of progress, uncertainty remains. The exact number of spiral arms is still debated. Some models suggest four major arms. Others favor two dominant arms with many branches and spurs. Distances to the most remote regions remain difficult to measure. Dust continues to veil parts of the disk. The Milky Way's true shape is still being refined. It is not a finished diagram, but a living sketch. The Gaia spacecraft has transformed this effort, mapping the positions and motions of more than 1 billion stars. Its data reveals subtle ripples in the disk waves of motion left behind by ancient impacts and arcs of stars drifting through the halo. These details add depth and texture, showing the Milky Way not as a static object, but as a galaxy with scars, with rhythms, with growth. Its shape is not a snapshot frozen in time, but a story unfolding over billions of years. And yet, for all this complexity, one truth stands clear. The Milky Way is immense. From the dense bulge at its core to the faint reaches of its halo, it stretches across hundreds of thousands of light years. Its spiral arms curve gracefully around a bright center. Its bar channels stars inward. Its halo fades gently into intergalactic space. It is not simply a band of stars overhead. It is a layered, dynamic system. To live within it is to inhabit something far larger than easy comprehension, a structure so vast that we can perceive only fragments at any given moment. The true shape of the Milky Way is therefore both a scientific achievement and a humbling reminder. A fact because we can describe its disk bulge arms and halo with increasing precision. A reminder because we can never step outside to see it whole. Our perspective will always be partial. Our maps will always be incomplete. And yet, through patient observation, the unseen becomes visible. The hidden form slowly emerges. It is a triumph of human curiosity, a reaching beyond our senses to grasp the larger structure that carries us. So when you look up on a clear night and trace the glowing band overhead, you can imagine more. Picture the wide, thin disk spiraling outward from a dense center. Picture the bulge glowing with ancient stars. Picture the bar stretching across the core. Picture the arms curling away into darkness. And beyond all of that picture, the halo faint, vast, and extending far beyond the light. That is the Milky Way's true shape. Not just the band you see, but the immense system it represents. And though you will never view it from the outside, you live within it, a quiet part of its form orbiting gently as the galaxy slowly turns. When most people think of the Milky Way, their attention rests on the glowing disk, the spiral arms, the bright central bulge, or the nebulae scattered across the sky. But the galaxy does not end where the light fades. Far beyond the visible disk lies a vast, nearly invisible region, the halo waiting to be explored further. This halo does not shine with the concentrated brilliance of the spiral arms. Instead, it exists as a quiet, ghost like realm, faint, elusive, and vast. It is populated by scattered stars, ancient clusters, and an overwhelming presence of dark matter. Though subtle and difficult to see, the halo is as essential to the Milky Way as the bright disk itself. Without it, the galaxy would not remain bound. The challenge in studying the halo lies in its nature. Unlike the disk where stars gather densely, halo stars are spread thinly across an enormous volume of space. Imagine walking into a forest where the trees suddenly stand miles apart. From where you stand, it might feel almost empty, yet the forest still stretches endlessly around you. That is what the halo is like: vast, diffuse, and deeply significant. Its diameter may span hundreds of thousands of light years, perhaps approaching 1 million, if its outermost influence is included. Within this immense sphere lies the faint scaffolding that defines the Milky Way's true reach. Among the most striking inhabitants of the halo are globular clusters. These are tightly bound, spherical swarms of stars, some containing hundreds of thousands, even millions of suns. Unlike the younger open clusters scattered through the disk, globular clusters are ancient. Many are more than 10 billion years old. They are relics of the galaxy's youth survivors from an era when the Milky Way was still taking shape. Orbiting far above and below the disk, in long looping paths, they form a loose shell around the galaxy, markers of its earliest history. From Earth, some globular clusters appear through small telescopes as soft, fuzzy patches of light. Through larger instruments, they resolve into glittering swarms breathtaking in their density. Each cluster is like a fossil embedded in the halo, preserving the memory of the galaxy's first chapters. But stars and clusters are only part of the halo's story. Surrounding the Milky Way is an enormous reservoir of gas extending far beyond the visible disk. This gas is extraordinarily thin, far more tenuous than the air we breathe. Yet, because it fills such a vast volume, its total mass is significant. Observations in ultraviolet light and X rays have revealed a hot, diffuse corona of gas stretching hundreds of thousands of light years into space. Some of this material may be left over from the galaxy's formation. Some may be slowly accreted from the intergalactic medium. It is not smooth or uniform. Clouds drift through it nearly invisible, except when they reveal themselves by absorbing the light of distant quasars shining from far beyond the Milky Way. These clouds are like phantoms in the halo detectable only when backlit by the deeper universe. One of the most famous of these ghostly features is the Magellanic Stream. It is a long ribbon of gas torn from the large and small Magellanic Clouds, two dwarf galaxies orbiting the Milky Way. This stream arcs across hundreds of thousands of light years, winding through the halo like a trail of vapor. Its existence shows that the halo is not a passive shell. It is active, shaped by gravity interaction and flow. Other stellar streams lace the halo as well. These are the remains of smaller galaxies that the Milky Way has consumed over billions of years. As a dwarf galaxy is captured, tidal forces stretch it apart, scattering its stars into long, coherent arcs. These streams persist for immense spans of time, scars written across the halo, telling stories of mergers and growth. The Sagittarius stream, for example, is the shredded remnant of the Sagittarius dwarf galaxy, currently in the process of being absorbed. By mapping these streams, astronomers reconstruct the Milky Way's turbulent past, learning how the halo was built piece by piece from countless smaller systems. At the heart of the halo lies its greatest mystery, dark matter. Invisible and undetectable, directly it nevertheless dominates the mass of the galaxy. The motions of stars and gas cannot be explained by visible matter alone. Only by invoking a vast halo of unseen material do the observations make sense. This dark matter halo likely extends far beyond the stars and gas enveloping the Milky Way in an invisible cocoon. Its true nature remains unknown, whether exotic particles, new forms of physics, or something yet unimagined. But its influence is undeniable. It shapes the galaxy's motion, holds its structure together, and quietly defines the full extent of our galactic home. Without this vast halo, the spiral arms of the Milky Way would not endure. The galaxy would slowly unravel its stars, drifting away into space. In this sense, the true shape of the Milky Way is defined less by the stars we see and more by the invisible dark matter halo that binds everything together. Because the halo is so sparse and faint, studying it requires ingenuity. Astronomers search for subtle tracers, RR Lyrae, variable stars, blue, horizontal branch stars, and distant quasars whose light passes through halo gas. By examining how that light is absorbed, scattered, or shifted, they infer the presence of matter that cannot be seen directly. Space telescopes such as Hubble have played a crucial role detecting ultraviolet signatures from hot halo gas and mapping its reach. Each observation adds a quiet fragment to the picture, revealing the faint architecture that supports the entire galaxy. The halo also serves as a bridge between the Milky Way and the greater universe. It is the region where our galaxy exchanges material with intergalactic space, slowly pulling in fresh gas from cosmic filaments and releasing enriched material through outflows driven by supernova explosions. This circulation keeps the galaxy alive. It feeds future generations of stars while dispersing the remnants of older ones. Without the halo, the Milky Way would be a closed system, gradually exhausting its supply of star forming material. With it, the galaxy remains connected to the vast cosmic web, participating in processes far beyond its visible boundaries. In this way, the halo can be thought of as the Milky Way's memory. Its globular clusters preserve the earliest chapters of galactic history. Its stellar streams record ancient mergers and long forgotten collisions. Its dark matter maintains the invisible framework laid down during formation, and its gas links the galaxy to the wider universe beyond. Though faint and ghost like, the halo carries some of the deepest truths about what the Milky Way is and how it came to be. To study the halo is to read the margins of the galaxy's story, the traces left behind long after the main body took shape. Of course, none of this is obvious from Earth. The halo does not blaze across the night sky. You cannot point to it with the naked eye. It reveals itself only through careful measurement, patient analysis, and quiet inference. Yet once you know it is there, your image of the galaxy changes. The Milky Way is no longer just a bright disk of stars. It becomes a layered structure, luminous at its core, yet wrapped in vast invisible extensions. The halo transforms the galaxy from a thin band into a sprawling three-dimensional form, reaching deep into the darkness with ghostly clouds and unseen mass. What makes the halo so compelling is that it stretches our idea of what a galaxy truly is. The disk and spiral arms are familiar and easy to imagine. The halo is harder to grasp because it is defined as much by absence as by presence. It reminds us that the galaxy's boundaries are not sharp and that its true form extends far beyond what glitters in the night. Within this shadowed realm, the galaxy continues to evolve. Streams keep falling inward. Gas continues to circulate. Dark matter silently shapes the paths of stars. The halo is not static. It is active, dynamic, and ever-changing. To imagine it is to picture the Milky Way breathing, expanding, and contracting, absorbing and releasing, woven into the larger currents of the cosmos. So, when you think of the Milky Way, do not stop at the glowing arms or the bright core. Imagine also the faint, ghostly halo filled with ancient clusters and invisible matter stretching far beyond the stars you see. Picture the streams threading through it, the clouds drifting in silence, the dark matter shaping unseen paths. That is the galaxy's full body, not just its shining surface, but its hidden form. To understand the halo is to glimpse the Milky Way's deeper nature, quiet, vast, and enduring. And when you widen your view even further, it becomes clear that the Milky Way does not exist alone. Surrounding it are smaller companions, dwarf galaxies moving in complex orbits, bound by gravity in a slow cosmic dance. Some are bright and familiar. Others are faint, barely detectable, their stars stretched thin across the sky. Together, they form a community, a neighborhood of galaxies whose interactions continue to shape the Milky Way's past and quietly guide its future. Among the Milky Way's companions, the most familiar are the large and small Magellanic Clouds. From the southern hemisphere, they appear as soft, irregular smudges of light, faint patches in the darkness, almost like fragments that have drifted away from the Milky Way itself. Long before their true nature was understood, sailors used these glowing clouds as guides across the oceans. They were steady landmarks in the southern sky, later named after the explorer Ferdinand Magellan, who described them during his voyage around the world. Today, we know they are dwarf galaxies in their own right. Each contains billions of stars bound together by gravity orbiting our galaxy at great distances. The Large Magellanic Cloud lies about 160,000 light years away. The Small Magellanic Cloud is a little farther, roughly 200,000 light years from Earth. Neither has a neat spiral shape. Both are irregular, stretched, and distorted by their ongoing interactions with each other and with the Milky Way's immense gravitational pull. These galaxies are not static companions. They move, they orbit, and as they do, they are slowly stripped of material. Streams of gas trail behind them, the most famous being the Magellanic Stream, a long ribbon of hydrogen that arcs across a vast portion of the sky. This stream is evidence of a gravitational tug of war, a slow exchange that reminds us galaxies are not rigid islands, but fluid systems constantly reshaped by interaction. Within the Magellanic Clouds themselves, star formation is intense. Their rich supply of gas fuels vast stellar nurseries. The Tarantula Nebula, located in the Large Magellanic Cloud, is one of the most active regions of star birth known. Their massive stars form in dense clusters, flooding their surroundings with energy and light. Beyond these two well known companions lies an even larger population of satellites. The Milky Way is surrounded by dozens of smaller dwarf galaxies, many of them extremely faint. Some are so diffuse that their stars barely stand out against the background of the galaxy itself. These ultra faint dwarfs may contain only a few thousand stars held together by halos of dark matter. They are like tiny lanterns at the edge of the Milky Way's influence, barely glowing yet gravitationally bound. In recent decades, deep sky surveys have revealed many of these hidden companions, showing that the Milky Way's family is far larger than once believed. Each new discovery adds depth to the picture of a galaxy surrounded by a retinue of smaller neighbors. These dwarf galaxies are not merely passive ornaments. Over billions of years, the Milky Way has consumed many of them. As smaller galaxies fall inward, tidal forces stretch them apart, scattering their stars into long streams that wrap around the galaxy. The halo is filled with these remnants, quiet traces of past mergers. The Sagittarius dwarf galaxy is one such example. It is currently being dismantled, its stars pulled into a vast ribbon that encircles the Milky Way. In this sense, the halo is not only a place of quiet darkness, it is also a record of past encounters, a kind of graveyard where the remains of former galaxies linger. The interactions between the Milky Way and its companions are subtle but powerful. As dwarf galaxies orbit, they disturb the larger disk, sending ripples through it. Some of the warps and waves observed in the Milky Way's structure may be echoes of these encounters. The Large Magellanic Cloud, in particular, is massive enough to exert a noticeable influence. Recent studies suggest that the Milky Way itself is slightly shifted by its presence, the two galaxies tugging on each other as they orbit a shared center of mass. It is a quiet reminder that even enormous systems are shaped by their surroundings. Dwarf galaxies are also valuable to astronomers because they offer insight into dark matter. Their stars move in ways that suggest dark matter dominates their mass even more strongly than in large galaxies. By studying these motions, scientists gain clues about the invisible substance that structures the universe. Each dwarf becomes a natural experiment, a small, simple system that helps illuminate a profound mystery. What makes these companions even more intriguing is their diversity. Some, like the Magellanic Clouds, are rich in gas and actively forming stars. Others are quiet and ancient, their gas long since stripped away, leaving behind only dim, aging stars. Some are stretched and irregular shaped by tidal forces. Others are compact and faint, barely holding themselves together. Together they show that the Milky Way does not exist in isolation, but as part of a living, interacting community, a reminder that galaxies grow not only by forming stars, but by gathering, absorbing, and transforming the smaller worlds around them. Others take on a more rounded form, almost spherical, like miniature versions of elliptical galaxies. Together, these small companions reveal something important. Even at modest scales, galaxies can appear in many shapes molded by their histories and environments. For the Milky Way, these dwarfs represent both past and future. In the distant past, many of them have already merged. Their stars are now woven so thoroughly into the galaxy that they can no longer be distinguished from the rest. In the far future, others may follow the same fate. Over billions of years, the Milky Way will continue to grow by absorbing its companions, slowly adding their stars and gas to its own vast body. This process is imperceptible on human timescales, yet relentless on cosmic ones. It is how large galaxies evolve, built patiently from smaller pieces. This relationship between the Milky Way and its dwarfs mirrors a larger pattern in the universe. Galaxies rarely exist alone. They gather into groups and clusters bound together by gravity. The Milky Way and Andromeda are the dominant members of the local group, but around them swarm dozens of smaller galaxies. The dwarfs that orbit the Milky Way are part of this structure, a smaller pattern nested within a larger one. It is a kind of cosmic echo, motion repeating itself across scales, small galaxies orbiting large ones just as large galaxies orbit each other. From Earth, this presence is subtle. Aside from the Magellanic Clouds, most of these companions are invisible without telescopes. Yet knowing they exist changes how the night sky feels. The Milky Way is no longer a solitary island of stars, but the center of a quiet family, surrounded by neighbors moving gently through the dark. Each of those companions contains its own stars, its own systems, perhaps even its own distant histories of life. As telescopes grow more sensitive, more dwarf galaxies continue to be discovered. Some are so faint that until recently they were completely hidden. Their stars are spread so thinly that they blend into the background of the Milky Way itself. By carefully analyzing stellar motions, astronomers tease out their presence. Each new discovery suggests there may be many more still drifting unseen in the shadows. The census of the Milky Way's companions is not finished. The dance continues, and the partners are still being counted. These discoveries offer a glimpse into the early universe. Long ago, small galaxies were common, merging again and again to form larger systems. The Milky Way is the product of countless such encounters. The dwarf galaxies we see today are survivors' fossils from a time when galaxies were young and far smaller than they are now. To study them is to look backward across billions of years toward the building blocks of cosmic structure. So when you imagine the Milky Way, do not picture it in isolation. Imagine the Magellanic Clouds drifting nearby, their gas stretched into long, luminous streams. Picture faint dwarf galaxies circling far beyond the visible disk. See the stellar streams, the lingering traces of past companions wrapping silently around the galaxy. Together, they form a dynamic system, a slow dance of giants and dwarfs, a story of growth through interaction and time. And though the Milky Way may appear calm, when you look up at the sky, it is anything but still. Every star you see is moving. Every cloud of gas, every cluster, every distant companion is in motion. The entire galaxy is rotating an immense whirlpool of stars, turning with such balance that it has remained intact for billions of years. Our own sun is part of that motion. At this very moment, as you listen, the solar system is orbiting the galactic center at a speed of nearly 828,000 kilometers per hour. That speed sounds impossible at first. And yet, because the distances involved are so vast, the motion unfolds with extraordinary patience. Even moving at more than 800,000 kilometers per hour, the Sun takes roughly 225 million years to complete a single orbit around the center of the Milky Way. This span of time is often called a galactic year. Since its birth about 4.6 billion years ago, the Sun has completed only around 20 such orbits. In that time, continents on Earth have drifted across the planet. Mountains have risen and eroded. Entire branches of life have appeared, flourished, and vanished. A single galactic year is longer than the entire history of complex animals on Earth. As astronomers began to measure stellar motions with greater precision, they uncovered something deeply unexpected. Stars far from the galactic center were moving just as quickly as stars much closer in. According to familiar gravity, this should not happen. In our solar system, inner planets race ahead, while outer ones move more slowly. Mercury completes its orbit in months. Neptune takes more than a century, but the Milky Way does not behave like a scaled up solar system. Instead, its rotation curve is nearly flat. Stars tens of thousands of light years from the center circle at almost the same speed as those deep within the disk. This discovery changed astronomy. If only visible matter were present. Stars, gas dust, the outer regions of the galaxy would not be held tightly enough. They would drift outward, and the galaxy would gradually unravel. The fact that this does not happen tells us something profound. There is far more mass than we can see. An immense halo of dark matter surrounds the Milky Way, extending well beyond the visible stars. This invisible mass provides the additional gravity needed to hold the galaxy together as it spins. Without it, the galaxy's rotation would tear it apart. The idea of dark matter emerged in the 20th century as astronomers like Vera Rubin measured rotation curves in galaxy after galaxy. The same pattern appeared everywhere. Spiral galaxies all rotated as if they contained much more mass than their light revealed. The conclusion became unavoidable. Galaxies are dominated by unseen matter, outweighing visible stars by several times over. What dark matter actually is remains one of the greatest open questions in physics. It does not glow, it doesn't absorb light, it reveals itself only through gravity. Yet without it, the Milky Way and galaxies like it could not exist in their present form. Even aside from dark matter, galactic rotation is remarkably subtle. The Milky Way does not spin like a solid disk. Stars and gas move along paths shaped by the galaxy's overall gravitational field. Stars closer to the center complete their orbits in fewer years because their paths are shorter, not because they move dramatically faster. This creates a gentle differential rotation where inner regions slowly lap outer ones over time. If spiral arms were simply collections of the same stars, this differential motion would wind them tightly and erase them. Instead, the arms persist because they are density waves patterns moving through the disk, compressing gas and igniting new stars as they pass. From our position inside the galaxy, all of this motion is almost impossible to sense. Constellations appear fixed. The night sky changes only over thousands of years. But on galactic timescales, nothing is still. The sun drifts along its orbit, gently bobbing above and below the galactic plane. Star clusters move together, then slowly disperse. Gas clouds swirl, collide, and collapse. Streams of stars arc across the halo remnants of ancient mergers. The Milky Way is alive with motion. To imagine this rotation picture, a vast disk 100,000 light years wide, filled with hundreds of billions of stars. Each one is a point of light circling the center, not rigidly, but in a flowing, coordinated dance. At the core, the central bar channels stars and gas. Spiral arms curl outward, the dark halo enfolds everything. Gravity holds this motion in balance, the outward tendency of rotation matched by the inward pull of mass. Because of this balance, the galaxy endures. Stars live and die. Gas recycles, new generations are born. Yet the overall structure remains stable across billions of years. Even collisions with smaller galaxies ripple through the system without destroying it. This resilience is a testament to gravity's quiet power. Still, mysteries remain. The precise shape of the dark matter halo, the detailed structure of the rotation curve, the influence of satellite galaxies like the Large Magellanic Cloud, All are active areas of research. The Milky Way's rotation is steady, but full of nuance. Even the sun's own path is not perfectly circular. It is slightly elongated, carrying it closer to and farther from the center over immense spans of time. And as you listen now, there is something quietly humbling to consider. You are moving. You are carried with the Earth around the Sun at about 30 kilometers per second. At the same time, you and the Sun are sweeping around the galactic center at more than 200 kilometers per second. Add to this the motion of the Milky Way within the local group, and the local groups drift through the larger cosmos, and it becomes clear that you are part of a cascade of motion layers of movement nested within one another. What feels like stillness is in reality constant travel, a journey guided quietly by gravity's hand. From Earth, we cannot sense this motion directly. The ground beneath your feet feels steady. The sky appears calm, yet the motion is real and it can be measured. Spectroscopy reveals subtle Doppler shifts in starlight, showing whether stars are moving toward us or away from us. Radio observations of hydrogen trace the slow rotation of the galactic disk, and missions like Gaia, with its extraordinary precision, map the positions and velocities of stars in 3 dimensions. With each improvement in measurement, the picture sharpens. A galaxy rotating smoothly, held together by a balance of visible stars and invisible mass. When astronomers look beyond the Milky Way, they see the same pattern repeated. Spiral galaxies turn gracefully, their arms winding around dense centers. Their rotation curves remain flat, just like ours. The conclusion appears universal. Galaxies spin without flying apart because they are embedded in halos of dark matter. In this sense, the Milky Way is not unusual. It is part of a vast family governed by the same hidden framework that shapes galaxies across the universe. And yet there is something quietly reassuring about this knowledge. It tells us that we live inside a structure that is stable on timescales far beyond human history. Civilizations may rise and fall, climates may change, species may come and go, but the Milky Way continues to rotate. Stars orbit, spiral arms persist. The dark halo holds everything in place. You are part of that rhythm carried along in a motion too vast to feel, yet too fundamental to ignore. The galaxy spins, and you spin in with it, moving silently through the dark. When astronomers first attempted to weigh the Milky Way, they began with what they could see. Billions of stars scattered across the disk and bulge. Clouds of gas and dust rich with potential for new stars. Globular clusters glowing nebulae, and regions of active star formation. All of this visible matter was carefully tallied. But when these numbers were compared with how fast the galaxy rotates, something was wrong. The visible mass was not enough. Stars at the outskirts were. It is the unseen framework of the galaxy, a silent skeleton that gives shape, balance, and endurance to everything we can see. The idea that an invisible presence shapes the Milky Way may sound strange at first, yet the evidence for it arrives from many directions at once. Gravitational lensing shows distant light bending around unseen mass. Measurements of the cosmic microwave background reveal that this hidden matter was essential in the earliest moments of structure forming in the universe. Computer simulations of galaxy formation only succeed when dark matter is included. Without it, galaxies fail to take shape at all. The Milky Way is not special in this regard. It is simply one example of a universal rule. Dark matter appears to be woven into the fabric of cosmic evolution itself, and yet its true nature remains unknown. One possibility is that dark matter is made of undiscovered particles, entities beyond the familiar particles of ordinary matter. Physicists have proposed candidates such as weakly interacting massive particles or actions, each with unusual and subtle properties. Another possibility is even more radical, that gravity itself behaves differently on the largest scales, requiring revisions to our deepest theories. Experiments around the world search for answers. Detectors buried deep underground listen for faint whispers of passing particles. Space based instruments scan the heavens for rare signals. Particle accelerators probe extreme energies, hoping to reveal new forms of matter. So far, dark matter remains elusive. We see its fingerprints everywhere, but never the hand itself. For the Milky Way, dark matter's role is not just abstract, it is deeply practical. Without it, the Sun would not orbit the galaxy as it does. The spiral arms would not endure, the halo would not exist. Dark matter's gravity binds the galaxy together, holding hundreds of billions of stars in a coherent whole. It allows the Milky Way to spin without flying apart. Every rotation curve traced, every stellar stream mapped, every motion measured in the halo is shaped by this unseen presence. From Earth, of course, you cannot point to dark matter in the night sky. You see stars, planets, and glowing clouds of gas. But once you know it is there, your picture of the galaxy changes. Each star becomes only part of a larger structure. Around it lies an invisible cocoon of gravity, silently guiding its path. The Milky Way becomes layered, bright and familiar on the inside, vast and hidden on the outside. Dark matter also shapes the galaxy's relationships with its neighbors. The slow dance of dwarf galaxies around the Milky Way follows the contours of the halo. Streams of stars pulled from disrupted companions trace invisible pathways through space. Even the distant future encounter with Andromeda will be governed first by the interaction of their dark halos long before their visible disks ever touch. In this way, the Milky Way is defined as much by what cannot be seen as by what can. Some describe dark matter as scaffolding, others as glue, others still as the foundation of the cosmic web. However it is imagined, its role is indispensable. Galaxies are not random gatherings of stars. They are bound systems formed and sustained by invisible mass. Without dark matter, the universe as we know it would look profoundly different. Perhaps it could not exist at all. The fact that we do not yet understand its nature does not weaken its reality. Its effects are written across the cosmos in motions, patterns, and distributions that defy any other explanation. The search continues. Telescopes watch for faint signals that might betray rare interactions. Detectors listen in silence beneath the earth. Colliders push the boundaries of energy and theory. Each experiment adds another step to the journey. Meanwhile, astronomers continue to map the Milky Way's dark matter halo indirectly. With exquisitely precise measurements of stellar motion missions like Gaia, trace the galaxy's gravitational landscape, slowly revealing how mass seen and unseen is arranged. The invisible hand remains hidden, but its presence is everywhere, and in its quiet influence, the Milky Way holds together, spinning gently through the dark. Simulations take these observations and compare them with models testing different shapes, densities, and distributions of mass. From this careful matching, a picture slowly emerges, not finished, but growing clearer with time. A vast, dark halo extending far beyond the visible stars, quietly guiding their paths through space. For those who prefer metaphors, dark matter can be imagined as the stage on which the galaxy's story unfolds. The actors, stars, planets, nebulae are brightly lit and easy to see. The stage itself remains hidden, yet without it, the performance could not exist. This unseen framework shapes every orbit, every spiral, every slow motion of the Milky Way. It does so without light, without sound, without spectacle, only through gravity. And while the mystery remains unresolved, there is a quiet reassurance in what we can know. The galaxy spins steadily. Its arms hold their shape. Its halo stretches wide. All of this happens because of dark matter. Even if we never learn exactly what it is, we can still appreciate what it does. It is the unseen companion of every star, the silent partner to every orbit, the invisible architect of our galaxy. The Milky Way is a story written in light, but it is also a story written in darkness. Together, the two create the structure we call home. When you picture the Milky Way, it is natural to imagine a grand spiral, vast arms of stars sweeping outward from a bright central core. Somewhere within that immensity lies the sun. But the question of where we are in this structure is both humbling and quietly fascinating. Our solar system does not sit in a dramatic location. We are not embedded deep within one of the galaxy's major spiral arms. Instead, we reside on a modest spur, a smaller branch that extends between two larger arms. This region is often called the Orion Arm or the Orion Spur. It is not one of the Milky Way's primary highways of stars, like the Sagittarius or Perseus arms. It is more like a side road branching gently between them, a structure a few thousand light years long filled with a mixture of stars, clusters, and glowing clouds. From the inside, it feels immense. After all, even the nearest stars are light years away, and the spur itself stretches across distances far beyond ordinary imagination. Yet on the scale of the entire galaxy, it is small, one feature among many easy to overlook on a grand map. And still, this is our home. The sun, the earth, and everything familiar orbit quietly within this narrow structure. Many of the constellations that shape our night sky belong to this same neighborhood. Orion, with its bright belt of stars, lends its name to the spur. Stars in Cygnus Cassiopeia and parts of Perseus also trace regions of this local branch. When you look at these constellations, You are not just seeing random patterns. You are looking at nearby landmarks, stars that share our spiral address. Living on a smaller spur may have its advantages. The major spiral arms are crowded and energetic places. They host intense star formation, massive gas clouds, and many short lived brilliant stars. They are vibrant but also chaotic. Supernovae occur more frequently. Radiation levels are higher. Gravitational interactions are stronger. By contrast, the Orion Spur is relatively calm. The Sun orbits at a comfortable distance from the galactic center and away from the densest regions of the major arms. Some scientists suggest this quieter environment may have played a role in allowing life to develop on Earth. In a more violent neighborhood, conditions might have been far less forgiving. Still, the Orion Spur is far from empty. Within it lie some of the most familiar and beautiful sights in the night sky. The Orion Nebula, a glowing cradle of newborn stars, is part of our local arm. The Pleiades cluster, bright and unmistakable, resides here as well. The Horsehead Nebula, the Rosette Nebula, and countless other clouds of gas and dust mark places where stars are forming. These are not distant wonders glimpsed across the galaxy. They are nearby neighbors only hundreds or thousands of light years away. When you observe them, you are looking directly into the fabric of our own spiral arm. Our position also grants perspective. From the Orion Spur, we can look outward toward the Perseus arm, seeing it across a vast gulf of space. We can also look inward toward Sagittarius, where the galaxy grows brighter and denser as it approaches the center. This vantage point offers balance, a place not too crowded, not too isolated, from which the broader structure of the Milky Way slowly reveals itself. From this position, we are able to chart the galaxy, measuring distances, tracking motion, and slowly assembling a map of a structure far larger than any single viewpoint could reveal. It is not a dramatic location, but it is an exceptionally useful one. Over billions of years, the sun has not remained fixed. It has drifted through different regions of the Milky Way, following its long, steady orbit around the galactic center. In the distant past, it has likely passed through major spiral arms, moving slowly relative to the density waves that define them. Each passage would have brought change. Nearby bursts of star formation, higher radiation levels, subtle gravitational disturbances rippling through the solar system. At present, we find ourselves between those great arms in a comparatively quiet stretch of the disk. But on cosmic timescales, this calm is temporary. The solar system continues its journey, and tens of millions of years from now, it may once again cross into a busier region of the galaxy. The Orion Spur is not permanent. It is a transient feature shaped by the Milky Way's evolving dynamics. To imagine our place on this small spiral spur is to imagine balance. Yes, we are located on a minor branch rather than a grand arm. But that smallness carries advantages. It has offered stability, relative calm, and a clear vantage point from which observation becomes possible. It is easy to imagine that a more dramatic location closer to the galactic center or embedded within a brilliant spiral arm might be more impressive. Yet perhaps our modest address is precisely what allowed us to exist at all. Astronomers have used this position to extraordinary effect. From here, missions like Gaia are able to map the positions and motions of billions of stars, constructing a three-dimensional portrait of the Milky Way. Clear lines of sight in many directions have allowed precise measurements of parallax and the discovery of Cepheid variables, which serve as stepping stones to ever greater distances. The Orion Spur is not merely a place to live, it is a platform for discovery. From here, we can look inward toward the dense regions near the galactic core. We can look outward across the disk toward distant arms. From within the galaxy, we trace its form. On a more personal level, our location offers perspective. The stars scattered across the night sky are not random. They are part of a larger structure connected by their shared motion through the galaxy. When Orion rises on a winter night, its bright stars mark our own spiral neighborhood. When the Milky Way arches overhead, we are looking along the plane of the disk, peering through layers of arms, spurs, and clouds. The sense of isolation that sometimes comes with contemplating space softens with this realization. We are not drifting alone. We belong to a vast rotating system bound together with billions of other suns. And although the Orion Spur is not among the Milky Way's grandest features, it is rich in beauty. Its nebulae clusters and star fields offer some of the most striking views in the sky. Its relative calm has nurtured our planet. Its position has allowed us to understand more of the galaxy than we otherwise might have. Our place may be small, but it is not insignificant. It is one thread in the Milky Way's spiral tapestry. So when you think about our location in the galaxy, do not picture a lonely star adrift in darkness. Picture a star among billions resting on a quiet spur between mighty arms. Picture the Orion Nebula glowing nearby, the Pleiades shimmering like scattered jewels, and the great arcs of Perseus and Sagittarius stretching beyond. This is our place, modest but steady, ordinary yet essential. It is where we orbit, where we observe, where we reflect. And in this quiet region of a small spiral arm, life emerged. Consciousness arose, and the universe through us began to look back at itself. When we think about the Milky Way, it is tempting to imagine it as the entirety of existence, a vast island of stars filling the cosmos. But in reality, our galaxy is only one among many. The Milky Way does not travel alone. It moves within a family of galaxies bound together by gravity, each influencing the others across immense distances. Among these neighbors, one stands out above all others: the Andromeda Galaxy, a system as vast and complex as our own looming across intergalactic space. Together, the Milky Way and Andromeda form a pair, the two dominant members of what astronomers call the local group. Andromeda, also known as M31, lies about 2.5 million light years away. That distance is enormous by human standards. Yet, on the scale of the universe, it is close. Its faint glow, visible to the naked eye under dark skies, has traveled for millions of years to reach us, carrying with it the history of another galaxy. Through a telescope, Andromeda slowly reveals itself, not as a single object, but as a layered presence, spiral arms unfurling in faint arcs, a luminous core glowing with the combined light of countless stars. And beyond what the eye can easily follow, a halo stretching far into the dark. Andromeda is larger than the Milky Way. It may contain close to 1 trillion stars, and it is not standing still. At this very moment, it is moving toward us at hundreds of kilometers per second. Across the gulf of intergalactic space, the distance between our two galaxies is shrinking. In several billion years, they will meet. The idea of galaxies colliding can sound violent. Images of stars crashing into one another may come to mind. But space is vast beyond intuition. Even during a galactic merger, individual stars almost never collide. Instead, the encounter will unfold slowly and gracefully. The two galaxies will pass through each other. Their immense gravitational fields will tug and stretch. Stars will be pulled into new orbits. Gas clouds will compress, igniting waves of star formation. Over time, the chaos will settle into a single, larger system, likely an enormous elliptical galaxy. Our solar system will survive. It may be carried into a different region of space. It may orbit a new center altogether. The night sky over millions of years would change beyond recognition. Andromeda would grow larger and brighter, filling the heavens until the distinction between our galaxy and theirs disappears. This future is not catastrophic. It is ordinary on cosmic scales. Galaxies merge all the time. The Milky Way itself was built through countless such encounters. This is not an end, but a continuation of a process as old as the universe. Andromeda is not our only neighbor. Looks nearby lies the Triangulum Galaxy, also known as M33, smaller than both giants, yet still vast, containing tens of billions of stars. Its relationship with the Milky Way and Andromeda is complex. Some evidence suggests it orbits Andromeda. Other models see it as an independent member bound to both by shared gravity. Beyond these three lie dozens of dwarf galaxies. Some orbit the Milky Way, some circle Andromeda, others drift between loosely bound to neither. Together they form what astronomers call the local group, a gravitational community spanning roughly 10 million light years, a small neighborhood in the larger cosmic web. But even the local group is not alone. It belongs to a broader structure known as the local sheet, which itself is part of an even larger region, the Laniakea supercluster, a vast expanse stretching hundreds of millions of light years across. On these scales, the universe is not random. Galaxies are not scattered like dust. They trace filaments of dark matter and gas forming a web of structure. Clusters, groups, and superclusters connect like nodes in an immense network. The Milky Way is one small point in that web. Andromeda holds a special place in our awareness because it is one of the few galaxies we can see without instruments. On a truly dark night, far from city lights, it appears as a faint, elongated smudge in the sky, easy to miss, easy to underestimate. Yet that dim patch of light is another galaxy larger than our own, filled with hundreds of billions of stars. Its light has traveled for 5 million years to reach your eyes. It began its journey long before humans existed. Within that faint glow lies an entire universe of worlds. Spiral arms, star clusters, nebulae, a long history of birth and collapse, much like our own. Astronomers study Andromeda closely, comparing it to the Milky Way. The similarities are striking. Both are spiral galaxies. Both possess extended halos of dark matter. Both host numerous satellite galaxies, yet Andromeda bears signs of a more turbulent past. Its disk shows ripples from ancient mergers. Its halo extends even farther than ours. Its globular clusters and stellar streams trace a history of collisions and growth. In many ways, Andromeda is a mirror, a version of the Milky Way seen from the outside, and our relationship with it is not fixed. The distance between us continues to shrink. The future encounter is already written into the equations of gravity. Two galaxies drawn together over billions of years, moving not by intention, but by the quiet certainty of mass and motion. In roughly 4 to 5 billion years, the Milky Way and Andromeda will finally meet. Not suddenly, not violently in the way we imagine collisions on Earth, but slowly, inevitably, guided by gravity across unimaginable spans of time. Computer simulations show the first close passage will distort both galaxies. Their disks will stretch and bend. Long tidal tails of stars will be flung outward into space. What once looked like orderly spiral arms will become vast arcs smeared across the sky. Then the galaxies will separate again only briefly. Gravity will pull them back. Over billions of years, they will pass through one another multiple times, losing energy with each encounter. Eventually, they will settle into a single, larger galaxy. Astronomers sometimes call this future system Milkomeda. By then, the Milky Way, as we know it, will no longer exist. The sun, at that time, may be approaching the end of its life. Earth, if it still survives, would sit beneath a sky utterly transformed. The familiar band of the Milky Way would be gone. In its place, vast streams of stars would stretch overhead, unfamiliar constellations painted across a changing heaven. This future reminds us of something essential. Galaxies are not permanent. They grow by merging. They change by interacting. They are chapters in a much longer story of transformation. Beyond Andromeda, the universe is filled with galaxies of every kind. Tiny dwarfs barely holding themselves together. Massive giants containing trillions of stars. Some old, some young, some calm, others violently active. In many ways, the Milky Way is unremarkable. It is not the largest, not the most massive, not the oldest, but it is ours, and its fate is shaped by its neighborhood. Our place in the local group binds us to Andromeda. We are gravitational partners destined to diverge, whether or not life remains to witness it. This connection reveals a deeper truth about the universe. Structure exists in layers. Stars gather into galaxies. Galaxies gather into groups. Groups gather into clusters. Clusters form superclusters, all of it woven together by filaments of dark matter stretching across vast cosmic voids. To think about Andromeda is not only to think about a single neighboring galaxy, it is to think about the entire network in which we are embedded. The Milky Way is not an isolated island. It is part of an archipelago connected by gravity, history, and eventual destiny to everything around it. From Earth, the night sky gives us only hints of this structure. The Magellanic Clouds appear as faint smudges in the southern sky. Andromeda, a dim glow in the north, is the nearest giant. Beyond that, the other members of the local group are invisible to the naked eye. Yet knowing they exist changes the meaning of the stars above. Every point of light belongs not just to our galaxy, but to a larger context. A family of galaxies moving together through space. The night sky is not only a map of stars, but a window into a community. Each galaxy immense, each alive with stars, each bound into the same cosmic web. Reflecting on galactic neighbors shifts perspective. We are small within the Milky Way, smaller still within the local group, smaller again within the supercluster, and yet we belong to all of it. When you look up and notice the faint glow of Andromeda, you are seeing a companion, a galaxy mirroring our own, its light crossing millions of years to reach you, and beyond it lie countless others stretching into the depths of space. The universe is not empty, it is crowded, not solitary but communal, not static but always in motion. The Milky Way itself was not always as we see it today. Like every galaxy, it has a beginning. To understand its birth, we must travel back nearly 14 billion years to a universe utterly unlike the one we know. A universe with no galaxies, no stars, no planets, only a hot, dense, rapidly expanding sea of energy and particles. In the earliest moments after the Big Bang, the cosmos was opaque. Matter and radiation were tightly coupled, forming a glowing fog. As the universe expanded and cooled, it became transparent. Light was finally free to travel. Those ancient photons still surround us today as the cosmic microwave background, a faint afterglow of the universe's infancy. At that time, the universe was almost perfectly uniform. Almost. Tiny variations in density existed, differences of just one part in 100,000. These subtle irregularities were seeded by quantum fluctuations stretched across space during cosmic inflation. They were small, but they were enough. Over time, gravity amplified them. Matter began to clump. Dark matter, invisible but dominant, collapsed first, forming vast halos. These halos acted as gravitational wells, drawing in ordinary gas from the surrounding universe. As the gas fell inward, it cooled, it condensed, and eventually it ignited. The first stars were born. The earliest ancestors of the Milky Way were not graceful spirals. They were small, chaotic proto-galaxies, clumps of stars and gas bound within dark matter halos. They merged, frequently colliding, combining, growing larger with each encounter. Out of this long sequence of mergers and transformations, our galaxy slowly took shape, a structure built not in a single moment, but over billions of years, a product of gravity time and the quiet persistence of cosmic change. The first stars were unlike anything we see today. They were born into a young universe, made almost entirely of hydrogen and helium, with no heavier elements to limit their growth. Free from those constraints, many of these early stars grew enormous. Some may have reached hundreds of times the mass of our sun. They burned intensely, brilliant, unstable, and short lived. Within just a few million years, they exhausted their fuel and ended their lives in colossal supernova explosions. These were not quiet deaths, they were cosmic forges. In their final moments, they created and scattered heavier elements, carbon, oxygen, silicon, iron, into the surrounding space. With each explosion, the universe changed. It became richer, more complex. This marked the beginning of a great cycle. Stars formed, stars died. And with every generation, the raw material of the cosmos grew more varied. The Milky Way could not have formed without this process. Planets like Earth could not exist without it. Life itself depends on the heavy elements born in those earliest stellar deaths. As time passed, small proto-galaxies continued to merge. Each collision added stars, gas, and dark matter to the growing structure. The Milky Way did not appear all at once. It assembled gradually, piece by piece, through countless encounters. Some of the stars from those earliest fragments still shine today. They live in the halo and in ancient globular clusters far above the galactic disk. These stars are older than the disk itself, older than the spiral arms. Many are more than 12 billion years old, placing their birth close to the dawn of the universe. They are fossils, living relics of the galaxy's infancy. The growth of the Milky Way was not gentle. Galaxy mergers stretched stars into long streams. Gas clouds were shocked and compressed, igniting intense bursts of star formation. Central black holes were sometimes fed, growing slowly at the heart of emerging systems. Yet, even in these violent events, stars rarely collided with one another. Space is vast. The structures merged, not the individual suns. Over time, the Milky Way's bulge took shape. A dense concentration of old stars near the center formed during these early chaotic mergers. The halo grew as well filled with the remnants of consumed dwarf galaxies. Gradually, gas settled into a rotating plane. It cooled, it flattened, and from this disk, new generations of stars were born. By around 10 billion years ago, the Milky Way had become recognizable. A spiral galaxy with a bulge, a disk, and emerging arms. The Sun was not yet among them. Our star formed much later, about 4.6 billion years ago, long after the galaxy had matured. By then, countless stars had already lived and died, enriching the interstellar gas. The iron in Earth's core, the silicon in its rocks, the oxygen in its atmosphere, all were inherited from that deep galactic past. We are quite literally children of the Milky Way, born from material forged across billions of years. Astronomers piece together this origin story by studying the galaxy's oldest components. The ages and chemical signatures of globular clusters reveal when the earliest building blocks formed. Streams of stars in the halo trace the paths of long destroyed galaxies. The bulge contains stars of many ages, evidence of a turbulent youth. Each region of the Milky Way carries a fragment of memory. Together they form a history written in starlight. Computer simulations add another layer of insight. By recreating the early universe inside powerful models, scientists watch galaxies emerge from dark matter halos. They see gas fall, inward disks take shape, spiral patterns appear. The simulated galaxies resemble our own, confirming that the processes we infer from observation are grounded in fundamental physics. These simulations also reveal subtler forces: supernova feedback that regulates star formation, black holes that influence the flow of gas, quiet processes that shape galaxies over billions of years without dramatic flashes. The Milky Way did not grow alone. From the beginning, it existed within a cosmic environment. The cosmic web funneled gas toward it. Neighboring proto-galaxies collided and merged. Gravity bound it to companions, including Andromeda. Even the black hole at the center traces its roots to those early times. It may have begun as the remnant of a massive star growing slowly as the galaxy assembled around it. Its presence reflects a deep connection between galaxies and their central black holes. Both grow together, both evolve together. That quiet heartbeat has pulsed at the galaxy's core for billions of years. Thinking about the Milky Way's birth is both scientific and deeply personal. Scientifically, it explains the structures we see today: the disk, the halo, the arms, the bulge. Personally, it explains us. The atoms in your body were forged in stars that died long before the sun was born. The elements that make life possible were scattered across space during the galaxy's formation. Our existence is inseparable from that history. We cannot watch the Milky Way form. We cannot rewind time. But the evidence surrounds us in ancient stars, in stellar streams, in clouds of gas, in the black hole at the center. Each is a fossil, each a quiet witness, from small clumps of gas and dark matter to a vast spiral galaxy, from the first stars to a planet that can wonder about them. The journey is long, intricate, and astonishing, and the story does not end here. The Milky Way is still alive, still changing, still becoming something new. Its birth marked only the beginning of a long existence shaped by gravity, motion, and time. Even now, the galaxy continues to evolve through star formation, quiet mergers, and subtle interactions with its surroundings. To think about how the Milky Way was born is also to think about what it is becoming. Its past does not lie behind it alone, it echoes forward. When we picture the Milky Way, we often imagine a fixed image: graceful spiral arms, a dense glowing center, a faint halo stretching into darkness. But galaxies are not frozen structures. They are dynamic systems reshaped again and again across billions of years. Just as the Milky Way assembled from smaller fragments long ago, its future is written in the same language of gravity and merger. The clearest chapter of that future is already on its way. Across intergalactic space lies the Andromeda Galaxy, about 2.5 million light years distant. It is moving toward us at over 100 kilometers per second. The distance is vast, so the encounter will take billions of years, but on cosmic timescales, it is inevitable. The two largest galaxies of the local group are bound together. They will meet. Long before the collision itself, Andromeda will slowly grow brighter in our sky. Over millions of years, its spiral arms will stretch wider, becoming a dominant presence overhead. Eventually, the two galaxies will pass through one another, their structures distorted by immense gravitational forces. The word collision suggests violence, but stars are separated by such enormous distances that direct impacts will be rare. Instead, gravities will do the work. Orbits will be reshaped. Stars will be flung outward into long tidal streams. Gas clouds will collide, compress, and ignite waves of new star formation. For a time, the merged system will be chaotic and brilliant. Then slowly order will return. The final result is expected to be a massive, elliptical galaxy smoother and rounder than the spirals we know today. The familiar arms of the Milky Way and Andromeda will fade into memory, preserved only in the motions of ancient stars. What becomes of our solar system is uncertain. It may be carried outward into the galaxy's outskirts. It may remain closer to the new center. Either way, by then, the sun will be approaching the end of its life, expanding into a red giant before shedding its outer layers. For life on Earth, this future holds no relevance, but for the galaxy, it is a profound transformation. Andromeda is not the only influence shaping what comes next. Even now, smaller galaxies continue to fall inward. The Sagittarius dwarf galaxy is already being absorbed, its stars stretched into a long stream encircling the Milky Way. Other dwarf companions will follow over time, adding their stars and dark matter to the growing halo. The future of the Milky Way is not defined by a single event, but by an ongoing sequence of encounters. Each merger subtly alters the galaxy's structure. Each leaves behind faint signatures that can persist for billions of years. At the deepest level, even the heart of the galaxy will change. When the Milky Way and Andromeda merge, their central black holes will begin a slow dance of their own. Drawn together by gravity, they will orbit one another, losing energy over time, spiraling closer and closer. Eventually, they will merge into a single, more massive black hole. That moment will release an enormous burst of gravitational waves, ripples in space-time that will travel across the universe. No light will mark the event, but the fabric of space itself will carry the signal. When the motion settles, the new black hole will rest at the center of the merged galaxy, anchoring it, just as Sagittarius A anchors the Milky Way today. The galaxy's future, like its past, is a story of transformation rather than permanence. Structures form, structures dissolve, new patterns emerge. The Milky Way is not a finished object, it is a process, and the legacy of its birth continues forward, shaping what it will become long after the stars we know have faded from view. When we imagine the Milky Way, it is easy to think of it as something complete and permanent, a vast spiral of stars quietly turning through space. But galaxies are not frozen structures. They are living systems shaped by gravity time and constant interaction. Just as the Milky Way was born from smaller fragments billions of years ago, it also has a future shaped by inevitable change. The story of our galaxy does not end with its present form. It continues forward, written into the slow motion of the cosmos. The most dramatic chapter in the Milky Way's future is its encounter with the Andromeda Galaxy. Today, Andromeda lies about 2.5 million light years away. That distance feels immense, yet on cosmic scales, it is remarkably close. Andromeda is moving toward us at more than 100 kilometers per second, drawn inward by the shared gravity of the local group. Though the motion is imperceptible to us, the outcome is certain. In roughly 4 to 5 billion years, the two galaxies will meet. The word collision can be misleading. Space within galaxies is so vast that stars rarely collide directly. Instead, the two galaxies will pass through each other, their gravitational fields interacting in a slow, intricate dance. Spiral arms will stretch and twist. Long tidal streams of stars will be pulled outward. Clouds of gas will collide, compress, and ignite waves of new star formation. For millions of years, the night skies of any surviving worlds would be filled with unfamiliar patterns as Andromeda grows larger and more dominant overhead. Over time, repeated encounters will drain energy from the system. The two galaxies will eventually merge into a single larger structure, likely a massive elliptical galaxy. The graceful spiral arms we recognize today will fade, replaced by a smoother, rounder form. Astronomers sometimes call this future galaxy Milkomeda, a reminder that galaxies, like living organisms, evolve by union and transformation. For our solar system, the future is uncertain but not catastrophic. The sun may be flung outward into a more distant orbit, or it may remain bound closer to the merged center. Either way, the sun itself will be nearing the end of its life, by then expanding into a red giant long before the final merger completes. Earth, if it still exists, will no longer be habitable. The galactic drama will unfold long after life here has faded. The Andromeda merger is not the only change ahead. Even now, smaller galaxies are being absorbed into the Milky Way. The Sagittarius dwarf galaxy is in the process of being torn apart, its stars stretched into a long stream that wraps around our galaxy. Other dwarf galaxies follow similar paths. Over billions of years, the Milky Way will continue to grow through these smaller mergers, just as it has since its earliest days. As galaxies merge, their central black holes are drawn together as well. Sagittarius, the quiet giant at the heart of the Milky Way, will one day encounter Andromeda's own central black hole. The two will spiral inward, orbiting each other until they merge into a single, even more massive black hole. This event will release powerful gravitational waves, ripples in space-time, that will travel across the universe. Though invisible to human eyes, such waves are a profound signature of cosmic change. Looking even farther ahead, the future extends beyond the local group. After the Milky Way and Andromeda merge, the remaining nearby galaxies, including Triangulum, will continue orbiting within the same gravitational family. Over tens or hundreds of billions of years, these two may merge, forming a single massive galaxy. Beyond this region, the accelerating expansion of the universe will carry distant galaxies beyond visibility, leaving future observers isolated in a darkening cosmos. Galactic mergers are not acts of destruction, but of renewal. They recycle gas, redistribute stars, and build new structures. Without mergers, galaxies would never grow into the forms we see today. The Milky Way itself is the product of countless past unions stitched together from smaller systems long vanished. Its halo is filled with the remnants of these ancient encounters, quiet evidence of a dynamic past. To think about the future of the Milky Way is to recognize that even structures so vast are temporary. Spiral arms shift, stars drift, entire galaxies change shape. The Milky Way we see today will not exist forever, yet its transformation is not loss but continuation, a reminder that the universe is not static but alive with motion. The galaxy's future is already unfolding, written into the paths of its neighbors and the pull of gravity itself. And as we look up at the night sky, we are witnessing just one moment in a much longer journey. The Milky Way was born, it lives, and it will change. And in that slow, silent evolution, the universe continues to tell its story. Yet, even as these changes unfold, the forces behind them remain calm and dependable. Gravity works without urgency, drawing galaxies together across millions and billions of years, shaping the future with the same certainty that shaped the past. When you imagine the far future of the Milky Way, you can picture Andromeda slowly brightening in the sky, spreading wider across the heavens with each passing age. You can imagine long streams of stars stretched into graceful arcs, vast clouds of gas colliding and igniting new generations of suns, and central black holes spiraling inward toward one another. Eventually, the motion settles. The two galaxies merge into one. The story of the Milky Way is not only about spiral arms and drifting stars, it is also the story of us, of how atoms scattered across billions of years and enormous distances have gathered into living beings capable of looking back and wondering where they came from. At the heart of this story is stardust. The early universe began with only the simplest elements, hydrogen and helium, with faint traces of lithium. These were enough to form the first stars, but not enough to create planets, oceans, or life. The heavier elements, carbon that forms the framework of organic molecules, oxygen that fills our lungs, iron in our blood, calcium in our bones, were all created later, forged deep within stars. Inside stellar cores, lighter atoms fused into heavier ones, releasing the energy that made those stars shine. When stars reach the ends of their lives, they return these elements to space. Smaller stars like the Sun gently shed their outer layers, forming glowing planetary nebulae. Massive stars die in powerful supernova explosions, scattering enriched material across light years. Even rare events, such as the collisions of neutron stars, create the heaviest elements of all: gold, platinum, uranium, flung outward at incredible speeds. Every atom that makes up your body has passed through one or more of these cosmic processes. The nitrogen in your DNA, the phosphorus in your cells, the potassium that regulates your nerves, All were forged in stars that lived and died long before the sun existed. When we say we are made of stardust, it is not poetry. It is a literal description. The Milky Way is the ancestor of every living thing on Earth, not symbolically, but physically, through the transfer of atoms from stars to space, from space to planets, and from planets into life. Our solar system formed about 4.6 billion years ago from a cloud of gas and dust already enriched by earlier stars. Gravity drew that cloud inward, flattening it into a rotating disk. At the center, the sun ignited, beginning its long, steady life. Around it, planets formed from leftover material, colliding, merging, and settling into stable orbits. Earth was one of these worlds, shaped by countless impacts, heated and reshaped again and again until it cooled enough for oceans to appear. Within those oceans, chemistry gradually became biology, and biology grew into life. The elements forged in ancient Milky Way stars became molecules, cells, organisms, and eventually beings capable of awareness. This connection changes how we see the galaxy. It is no longer just a distant structure, traced in light years and mass. It is the source of our bodies, our breath, and our thoughts. To look up at the Milky Way is to look toward the place where your atoms were born. The stars are not strangers, they are ancestors, part of a long cycle of creation and return that made you possible. This realization is both humbling and grounding. It shows how small we are, one species on one planet, orbiting one star on a modest spur of a spiral arm among hundreds of billions of suns. And yet it also shows our belonging. We are not separate from the cosmos. We are made of the same matter, governed by the same laws, carried along by the same cycles. The galaxy is not something distant hanging above us. It exists within us, woven into every cell. The oxygen you breathe was created in a star billions of years ago. The carbon in your food once drifted through interstellar clouds. The iron in your blood was forged in the heart of a massive star. These are not metaphors. They are physical truths, direct connections between your body and the Milky Way. You are a small fragment of its immense story, alive briefly before your atoms return to the cycle once more. Even your awareness is part of that process, the galaxy through you becoming conscious of itself. The very ability to think about the galaxy, to measure its size, to imagine its form is itself a consequence of cosmic history. The neurons firing quietly in the brain are built from atoms that once existed inside stars. Consciousness is matter that has learned to observe itself. Light that once burned in stellar cores is now arranged into delicate patterns capable of thought. When you wonder about the Milky Way is in a sense wondering about itself. On a personal level, this connection can be deeply comforting. In everyday life, the universe can feel distant, immense, even overwhelming. But remembering that you are made of stardust is a reminder that you belong here. Your presence in the cosmos is not an accident, but a natural outcome of the same processes that formed stars and galaxies. The Milky Way is vast, yes, but it is also home. and you are woven into its fabric. Every star you see in the night sky is kin. Every atom in your body has traveled through the same cycles that sustain galaxies. You are not standing outside the universe looking in. You are inside it, living as part of the whole. The history of the Milky Way is not only a story of structure and mergers, it is also a story of individuals, of planets, ecosystems, and living beings that arise within it. Each person carries a fragment of that history. Each life is a unique arrangement of ancient atoms and lived experience. From the galaxy's perspective, we are small. From our perspective, the galaxy is immense. Yet the two are inseparably linked. The vast and the personal meet in the simple fact that we exist. When you look up at the night sky, try to sense that connection. See the stars not only as distant points of light, but as the sources of the atoms that make you. See the Milky Way not only as a structure in space, but as your ancestor. See yourself as part of its ongoing cycle, a temporary gathering of stardust that will one day return to the galaxy and become something else. This way of seeing does not diminish you. It places you. It grounds you in a story larger than any single life, yet intimately connected to each one. The personal scale is not about shrinking the galaxy down to human size. It is about expanding your sense of self to include the galaxy. It is about recognizing that your body, your thoughts, your life are part of a chain stretching back billions of years, part of a network spanning vast distances of space. To live is to participate in the Milky Way's continuing story, to carry its history forward, to reflect it back in the form of awareness. And perhaps that awareness is the galaxy's most remarkable creation. Stars burn, galaxies merge, black holes grow, but none of those processes involve reflection. Only here on one small planet, orbiting one ordinary star, did matter organize itself into beings capable of asking where they came from. The Milky Way made that possible, and through us, it comes to know itself in a way it otherwise could not. From stardust to awareness, the scale becomes personal, the immensity becomes intimate. The galaxy is no longer just our home, it is our origin and our essence. As the night deepens, the mind begins to drift. Just as the Milky Way drifts through space, it has carried us on a journey from its crowded center to its spiral arms, from its faint halo to its neighboring galaxies, from its ancient birth to its distant future. But in these quiet moments, it is no longer about numbers or measurements. It is about the feeling of belonging, the sense that you are resting beneath a sea of stars that stretches beyond sight and beyond imagination, yet somehow includes you completely. The Milky Way is not only above you, it is the substance of your being, the cradle of your atoms, the silent companion of your thoughts. When you lie back and look at the sky, what you see is not only light, but history. Each star carries a message from deep time. Each glow marks the end of a journey measured in light years. The band of the Milky Way itself is a kind of memory. Billions of suns woven together, their light overlapping into a soft, hazy glow. To gaze at it is to see time spread across the heavens, a reminder that the universe is always moving, always carrying its story forward. And in the stillness of the night, you can allow that vastness to wash over you gently, not as something overwhelming, but as something calm, steady, and deeply soothing. The galaxy is immense, yes, but it is calm. Its stars follow paths that take hundreds of millions of years to complete. Its spiral arms unfold slowly. Its halo extends in silence. Its neighboring galaxies drift closer over ages that feel almost timeless. Compared to the brief tempo of human life, the Milky Way moves without urgency. To rest beneath it is to sense that slowness, to allow your breathing to align with a rhythm far older and far greater, a rhythm that will continue long after any single life has passed. The sea of stars above can be imagined as a true ocean, each point of light a distant ripple, each cluster a gentle swell, each spiral arm a slow current. We are suspended within this ocean like a small vessel drifting on a surface that seems without end. And yet, within that vastness, there is peace. The galactic ocean is not chaotic. It is balanced, shaped by gravity, its motions smooth and harmonious. To picture yourself floating within it is to accept that you are carried, supported, held within the flow. There is nothing to struggle against, nothing to fear. The galaxy holds you in its currents, and you move with it naturally. Sometimes, when we speak of cosmic scale, it can feel distant or impersonal. Numbers grow so large they lose meaning. Distances stretch so far they feel empty. But viewed from another angle, those same scales can feel protective. The galaxy is so large that your worries become small by comparison. Its age is so deep that your anxieties cannot burden it. Its stability is so profound that it makes your place within it feel secure. The galaxy asks nothing of you. It simply exists, steady, luminous, expansive, and within that quiet existence, you are free to rest. Imagine now the slow rotation of the Milky Way. Not something you can see, not something you can feel directly, but something you know is happening. The sun carries you around the galactic center once every 225 million years. Even now, in this moment, you are moving along that path, a silent traveler on a journey that began long before humanity existed. The stars around you are fellow travelers, each following its own orbit, each guided by the same gravity. Together, billions of them form a dance that is patient and enduring. To know this is to feel part of something continuous, something unbroken. The spiral arms of the galaxy can be imagined as slow waves of light. They are not fixed structures, but moving patterns, places where gas gathers and stars are born. Over time, they will shift, fade, and reform. But in this moment, they curve outward with quiet elegance. Our solar system drifts between them within a gentle spur, a calm passage between brighter streams. To exist here is to be sheltered, to live in a region where life has been given time to emerge, where conditions allowed thought to grow and reflection to unfold. Above you, the Milky Way may appear as a simple streak of light, but if you could step outside of it, you would see its full form, a barred spiral stretching across 100,000 light years. Beyond the glowing disk, the halo would dissolve gradually into intergalactic space, linking us to the local group, to Andromeda, to Triangulum, to countless smaller companions. Beyond that, clusters and filaments extend outward, forming the great cosmic web that binds everything together. And here you are, one small being, beneath it all, looking upward, your awareness a quiet spark within that immensity. The galaxy is vast, but within its endless sea, your spark shines however softly, however briefly. As your thoughts begin to slow, you might allow yourself to imagine floating upward into that sea, rising gently past the clouds, past the thin edge of the atmosphere, beyond the familiar bounds of the solar system, and into the disk of stars surrounding you. Suns glow in every direction, more than could ever be counted, even across 1,000 lifetimes. Nebula drift like slow, colorful breaths in the dark. Star clusters glimmer softly, scattered like distant jewels. Long stellar streams curve through the halo, tracing ancient paths. You drift onward, passing beyond the Orion spur, gliding across spiral arms toward the quiet center where Sagittarius A rests as the galaxy's anchor. There is no urgency. You move without effort, weightless and calm. The galaxy does not surround you with touch, but with scale, with the deep assurance that you belong entirely within it. From this perspective, time begins to loosen its grip. Millions of years between orbits fade into insignificance. Billions of years of galactic history feel like a single slow breath. Even the future meeting with Andromeda no longer feels distant or threatening. It becomes simply another movement in the same unending rhythm. Galaxies merge, stars ignite, stars fade, black holes grow quietly, and through it all, the universe continues expanding, steady and patient. Within that rhythm, your own life finds its place. Your days and nights, your pauses and rests become gentle ripples in an ocean that endures far beyond any one moment. As your breathing slows, the galaxy seems to breathe with you. Each inhale mirrors the unfolding of a spiral arm. Each exhale echoes the quiet fading of a star, returning its substance to space. You are aligned with this motion, not apart from it, not separate. The galaxy is not something above you, it is something within you. The stardust that forms your body is the same stardust glowing in distant suns, the same matter drifting through nebulae, the same substance that will one day gather again to form new stars and new worlds. To rest beneath the Milky Way is to rejoin that cycle, to allow yourself to soften into its flow, to sleep as part of its vast, patient ocean. Now you can release the need to measure the urge, to calculate the habit of holding the galaxy in numbers. Measurements have their place, but they are not the whole experience. The whole is too large to fit inside data alone. It is felt instead in moments like this, lying beneath the night sky, imagining the sea of stars as a gentle cover around you. The galaxy is not something you must fully understand. It is something you can simply rest within, allowing its immensity to support you, its calm to settle you, its silence to quiet your thoughts. And so beneath this galactic ocean you drift, you breathe, you rest. The stars remain steady, the galaxy turns slowly, and you are carried within it. Tomorrow will arrive, and with it, the familiar world of waking life. But for now, the Milky Way is your horizon, your cradle, your endless sea. Its light is soft, its embrace is vast, its rhythm continues without effort. Let yourself drift with it, as stars drift, as galaxies drift, as time itself moves forward. You are safe within this motion, a small expression of something immeasurable, a quiet fragment of stardust resting beneath the galactic sea. Thank you for sharing this quiet journey through the galaxy. Together, we have moved across spiral arms and halos through clusters and clouds across time, stretching from the birth of stars to futures yet unseen. Along the way, the Milky Way has shifted from a distant band of light into something closer, something intimate, something you are part of at every level. The atoms in your body, the air moving through your lungs, the thoughts passing gently through your mind have all been shaped by the galaxy, carried from one generation of stars to the next until they arrived here in you. As you rest now, allow that sense of belonging to remain. The galaxy is immense, but you are not outside it. You exist within it, moving with it, orbiting in harmony with its rhythm. Each heartbeat, each breath, each drifting thought travels in the same currents that guide the stars. The Milky Way is not watching from afar. It is your home, your origin, your quiet companion. If this moment has brought you calm, if drifting through these ideas has helped you rest, you are always welcome to return whenever you need science spoken slowly, gently, with care. You are welcome here on any quiet night, beneath the stars, beneath the galactic sea. For now, if you haven't already let your eyes close, let the weight of the day fade away. Let the vast stillness of the Milky Way hold you. Sleep like the galaxy itself arrives when you release effort, when you allow yourself to be carried, when you trust that the universe continues its rhythm without needing anything from you. Good night. May the stars above and the stardust within keep you company as you drift into rest.